Start recording. Okay, we're good. So, yeah, so I was thinking we do these practice questions starting with center of mass, right? Starting with center of mass. I'll do a quick thing about like center of mass. So, I mean, I'm sure. Okay, anyways, I'll do a quick thing. Okay, so first thing we're talking about is center of mass. Pretty much if you have like a big complicated shape, and you want to know how it moves in like as a object in kinematics, and you do all those kind of things to it, well, you just pretend like it's a point mass but centered at the center of mass, right? And determining where that center of mass is not too complicated, but there's like steps to it, and that's what we're going to do, determining where the center of mass is. And then once you know where the center of mass is, well, then you can just do the whole like kinematic stuff just with the center of mass. Yeah. So that's pretty much it. Well, actually, I guess I'll leave that picture there, but it's not. Okay, whatever. Move it over a little bit. And so let's begin with these questions. I think, so this is momentum and its conservation. That's from the last test. And I think the last three questions here are on center of mass. So let's take a look at it. So 38 from chapter 9.
And 24 is a question too.
24 is the center of mass question? Okay.
Yeah.
Okay. Oh yeah, okay. Oh yeah, I remember seeing this when we were studying for the last one. Okay. So the first question is this. Okay, there's that, and then there's a diagram for it too. Okay. So a uniform piece of sheet metal is shaped as shown in this figure. Compute the x and y coordinate of the center of mass for each piece. Okay. So what we do is we can just if we're computing the x and y coordinates. So in general, the center of mass is here. So the position of the center of mass is 1 over the total mass, right? 1 over the total mass times the sum of the mass times the position for each one, right? So the center of mass for the whole thing is the sum of from I to n, if we have n items, right, of mi ri, right? So pretty much the average, right? That's kind of what we're computing. And so if we're computing the x and y component, we can separate this out into two of them, right? We can say the x value of the center of mass is 1 over the total mass times the sum from I to n of m I r x I, right? And the other one too. So y center of mass equals 1 over mass from I to r of mi r y I. There. Okay. So I'm pretty sure, let me think about this. Okay, so if we have masses, we don't know the mass of the whole thing, right? There's nothing else we know. So I guess we can just call each mass m. So there's the total, there's how many pieces? 1, 2, 3, 4, 5, 6. There's 6 pieces, right? So the total mass is 6m, right? Each one mass is m. And the positions, let me think. So the center of mass for each of these seems to be in the middle. So I guess that's where we're going to put the center of mass for each of them, because it's a square, it's a uniform piece, right? So those are the center of mass for each of these things. Now we just have to add them all together, right? So let's start with the x value, right? The x value. This is going to be 1 over, I'll still call it big M, right? Now the sum of mass times Rxi. So let's start with this piece right here. The x value of that piece is 5, right? And its mass is m, so it's 5m. Next one is 15m. Next one is 25m. Yep. Okay, and now this piece up here is another 5m. This piece up here is another 5m. And this piece right here is another 15m. Right? And that's that. And notice, so actually I will replace the big M with 6m. Notice I can factor out the So it's 1 over 6 times 1 over m. Well, that's kind of a too confusing way of saying it. But I can factor out an m from the top. 5 plus 15 plus 25 plus 5 plus 5 plus 15, right? M's cancel, so the m doesn't actually matter, right? We can still calculate it. So it's just 1/6 of 20 plus 25 is 45, 50, 55, 60, 70. So 1/6 of 70. Right? And so the x component is 70 over 6, which is 35 over 3, which is approximately 11.67. Okay, so the x component of the center of mass is going to be about on this line here. On this line, wow, I'm bad at drawing lines. That line there, 11.67, something like that, right? So now we got to figure out the y value. So it's a similar way, right? So we say the y value of the center of mass is 1 over the total mass times, well, I'll just write it again, the sum from I to n is the number of blocks we have, of mi r y I. So 1 over 6m times, now let's look at each piece. Each piece has a mass of m, and their y component is this. Okay, so the y component here is 5, 5, 5, so you have 3 5s here. So 5m plus 5m plus 5m. Then I have 15m, 15m, 25m, 25m. There. Okay, again, similar thing. I'm not going to factor out the m, but you can just see that the m's cancel, all these m's. So you factor out the m, boop, they all cancel, and now you just do 1/6 of 15, 30, 55, 55, 60, 80. So 1/6 of 80 is 40 over 3, which is approximately 13.3. So the y component of our center of mass is 13.3, so like here, and we said the thing was 11.6, so maybe like right there. So that looks like to be our center of mass for this object right there. And hopefully, oh no, there's no answer for this one because it's a even number, unless there is one here. Yeah, 11.7, 13.3. There you go. We're good.
Sorry to interrupt. Can we just retrace our steps
Yeah, for sure.
really quickly?
For sure, for
Thank
sure.
you.
So we have 6 masses here, right? 6 masses. We're trying to figure out what the center of mass of that whole object is, right? So the formula for center of mass, which can be broken up into x and y, is the center of mass, the position of the center of mass, is 1 over the total mass, which we said was 6m, and then times all of the masses and positions multiplied together, right? So for this block here, it was the mass is m, and I multiplied that by its, well, if we're doing just x position first, right? Its x position is 5, right? So it has a xi, or it has an rxi, or just rx, I guess, rx of 5, right? Or 5, yeah, 5. And the position, what you put inside of this summation is the mass times its position. So that would be that. That's mi. No, I keep saying I. Sorry, m times rx would be 5m, right? And so we do that for each of the positions. First of all, in the x direction, right? First in the x direction. So just thinking about the x position of all these blocks. Okay, so this one had 5. This one had 5. Yeah, 15, 25, 5, 5, 15. Just the x positions. Multiply each of those by m, right? That's what this is saying, right? And this is the x position one. And then just divide that by the total mass, right? Total mass is 6m, so you notice here, I can factor out an m. M's cancel, so it's actually just numbers. You can actually just calculate it. And so we got the x position of the center of mass. So RCM x is 11.67. And in a very similar way, we did the y value, right? So for each piece, we multiply its mass times its y position, and then add those all together, right? Add those all together, and then divide by the total mass, which again is 6m. So I did that. Multiplied each one, position times mass, factored out the m and canceled it with the 1 on the bottom. So 1 over 6 m, all that. And then added that all together, 1 over 6 times 80, and that ended up being about 13.3. So the y position, the RCMY, was about 13.3. So now I have an x and y position for my center of mass, and so I can just approximately plot it there. Okay.
Okay, thank you.
No problem, no problem. Okay, oh, well, that worked. So let's try the next one, 38. 30, oh my god, wow. Okay, I went flying. 38 is going to be next page. There it is. Okay, looks like a little bit of a long one, so let's see. Oh, this is not 38? Is that the right question?
I don't think the rest are center of mass. I looked through them and
Oh,
they're just like
none of the rest of them are center of mass questions?
there's just one question.
Oh. Okay. The rest of them are probably then this momentum and its conservation questions. Right? So maybe
Yeah.
let me look at them quickly, but no, I'm sure you're right. Let's see. This one is momentum and its conservation, yeah. And then 47 is yeah. Okay, so then I guess let's move on. Let's move on to chapter 10. That's the only center of mass question we got, I guess. Let's see. Is there anything from maybe from Springer's lecture that we can go through?
Yeah, he has pretty good examples.
Yeah, so I think we should do that. So this is not it. Okay. Yes, center of mass, center of gravity. Let's find an example.
5 was the web assign question. Like, if we could go through it, that would be nice.
A web assign question? We can, yeah.
Yeah. It's pretty long, but yeah.
Sure. Okay, I also found a good one from Springer. But yeah, what's the web assign question? What's the
25.
45?
Oh, 25, just
Oh.
below the one.
Oh, okay. Like from the textbook?
Yeah, from the textbook.
Oh, okay. 25. Oh yeah, this one. I don't think I got this one on the web assign, so let's see if we can figure it out now. Let's see what's going on. So, I can't really take a picture without getting that, but web assign I seem to just like, if I can't do it, I kind of just, I don't know. Once the mark is high enough, I just kind of give up on it. So
Yeah.
let's see if we can figure this out. So yes, I remember this being on the website. Explorers in the jungle find an ancient monument in the shape of a large isosceles triangle, as shown in that figure. The monument is made up of tens of thousands of small stone blocks of that density. The monument is that meters high, that meters wide at its base, and is everywhere 3.6 meters thick from front to back. Before the monument was built many years ago, all the stone blocks lay on the ground. How much work did the laborers do on the monument to put them in position while building the entire monument? Note the gravitational potential energy of an object Earth system is that, where y is the total mass of the object and ycm is the elevation of its center of mass above the chosen reference level. Okay. So we're looking for how much work was done by the laborers. So I think we're pretty much trying to figure out what's the gravitational potential energy of this, right? Of this piece. So UG equals M as in the whole mass, I guess. That's why they use capital M. I guess M is the total mass. G and then YCM. So the total mass, we don't know. Do we know the total mass? We can, I think.
We know the density, so you can
We know the density and we can find the volume. Yeah, we can find the volume. So we can find the total mass. Sure, we got that. And maybe we'll do that first. G we know. Then we also have to find the y component of the center of mass, right? The y component of the center of mass. So we don't actually have that yet. We do have that. We don't have that yet. I should do it in yellow. That's what we're looking for. So let's find the total mass first. Well, mass, so if we take this density, right, which is kilograms per meter cubed, to get mass, I'm going to have to multiply that by something meters cubed, right? So the volume of the whole thing, right? So let's figure out the volume. Well, the volume is going to be the area of the face times its thickness, right? So the area of the face is just base times height. So 64, I'll just write area of the face is base times height over 2, which is, well, I won't even put variables yet. And then the volume is going to be the area of the face times the thickness. I guess I'll do that, right? So what that is it's base times height over 2 times the thickness, right? Which is going to be 64.8 times, put a dot, times 15.7 times 3.6 all over 2. Okay, so the volume is going to be 64.8 times 15.7 times 3.6 divided by 2. So I got the volume to be 1,831.2 meters cubed. Okay, so we know the volume, and now to find the mass of it, well, we just multiply it by the density, right? So mass equals volume times density. Well, I don't know how to draw the row thing. I guess that's density. So the volume is 1831.2 times 3,800. Right. And so I'll just multiply that. Answer times 3,800. Okay, and so my final answer, is this in kilograms? Yes, this is in kilograms. So my answer is a very big number. 6,958,742.4 kilograms. Yeah. Okay, so that's our mass. We found our mass. Now, we need to find the center of gravity. And so the x position of our center, well, we don't need the x position of our center of gravity, sorry. Well, the x position would be right in the middle because it's symmetrical. The y position of the center of gravity would, I think that's something, there's a formula for it. I think it's in this thing.
It's like 1/3 the height.
I was thinking that. I was thinking.
It is the centroid. The center of mass, mass, I think is the centroid of the triangle.
Yeah. Okay. I see what you mean. So, are we? But I think there might be just a formula to find the centroid. I don't know the form.
Yeah, I remember like
Yeah, it's
asking.
height divided by
Yeah.
3.
Just the height
I
divided
think
by
I got it right.
For the y-axis of the centroid of the triangle is height divided by 3, and for the x-axis is base divided by 3.
base divided by 3.
For
That's
the
for-
x coordinate.
That's right. This is
okay.
1/3 of the height.
Essentially,
so
on y, it's height divided by
It's
3.
just 1/3 of 15.7. That's all it is, right?
Yeah.
Yeah.
Yeah. So pretty much. Well, I want to see the formula written though. I don't want to. What does anybody remember what chapter was in? Not rotational kinematics.
Somebody said no in the chat. That's how I know.
Yeah.
It's in that summary formula sheet in the
Is it?
Yeah.
physics chat.
I sent a picture in discussions. I think it's something similar to that.
Yeah. Let's see.
There's a formula sheet there. You guys are G's right now.
Okay, yeah, good. I just want to see it in writing. Yeah, so there you go. So this is... Oh, it's not letting me pick it up. Give it a second. No, it doesn't want me to pick it up.
I truly love my classmates who really do these things.
There. Okay. So, put it here. Hold on, I gotta erase these dots. Okay. So, centroid is there. The height of it is the height divided by 3. Okay, good. Same thing here. That centroid is the height divided by 3. Yeah, height divided by 3. Okay, so it makes sense. So just for any shape like that. I'll put this back here. So then our printer turned on. The center of mass, the y component will just be 1/3 of the height. So the YCM will be the height. Well, I'll just say the height divided by 3, which is 15.7 divided by 3, which is approximately 5.23. And it's in meters. Okay. And so now we can just try to plug everything into the formula, right? So UG equals the total mass times G times YCM. Well, it's not a vector, it's just a thing. So total mass, well, we'll just say it was total mass. Actually, every number we know. I just want to make sure this is actually going to get us work. So how would this get us work is M is kilograms, meters per second, and YCM
Force
is,
times distance.
yeah.
Force times distance. Because, yeah.
Yeah, okay.
Yeah.
Yeah, because this is giving us the rest of the units. Yeah, okay.
Yeah.
So I can just plug everything in. So this is 6,958,742.4 times 9. That's a G. 9.81 times 5.23. Okay, and that's going to be 6,950. Did I say 58 or 85?
We have to convert. So, did you convert the centimeters to meters? Because I think the. Never mind. My bad.
No, it's all in meters.
My
Yeah,
bad.
don't worry. 6,958,742.4 times 9.81 times 5.23. So I got 357,027,325.2 joules. And that would be the work done, I guess, because that's how much the potential energy was raised by. So 357 and 27.3252 kilojoules. That didn't really simplify things, did it? But it's fine. That might be the answer. Is that the answer to the question? Is that right?
It's, well, yeah. Should be. Because like this is the same thing I did and I got it right on the homework.
Okay. Good. Well,
It
there you
is.
go. Good. Okay, good. See, here we go. So maybe I shouldn't give up on Web of Science if I can actually do it.
Yeah, you should.
Well,
So,
too late
well,
now.
it's too late now. Yeah, so I was thinking a little bit too
Too
late to
late.
realize that. Yeah. Okay. So can't draw an equal sign for some reason. There you go. So anybody want to do a different question, like about like anybody's suggestion from this for center of mass? Pretty much that's what I want to focus on right now. So this was a center of mass
Yeah,
question.
you know that disc one? Like you cut out a circle out of a larger circle. That one, like I think it's still good to practice.
Oh, well, cutting out something of something. I have a question actually from Springer's. It's a center of mass with a negative mass with like a hole. So maybe
Yeah.
is that like we'll do a question like that? Yeah.
That's exactly. And like one's like the radius, half the radius of the other.
Yeah, let's see here. Let me just get this. So this might not be exactly the question you're saying, but it's definitely a similar process to solving this one. Let me find it here. Lecture notes. I just want the actual picture. This is from center of mass. Okay. So I'll just put this whole thing there. Okay. So here's the question from Springer's lecture. Okay. So two square slabs of steel with the same thickness are welded together as shown. The large piece has side length of 1 and a mass of 10. So I'll put that on the picture. So this has a side length of 1 meter, and I'll say oops, I'll say 10 kilograms. Okay. The smaller piece has a side length of 0.5 meters, and you don't know the mass of it. A circular hole centered on the piece of metal with radius centered on the piece of metal with radius 0.25. That's 0.25, 0.25. Tiny little writing. Okay, I'll just put an arrow. 0.25 meters. Is drilled into the metal. Where is the center of mass of the object? So with this one, when you have a piece being taken out of the of another larger piece, right? You can treat it as a negative mass. So you do the same thing, but you just call it a negative mass, right? So let's say we don't know any other information, right? 10 kilograms, no, smaller piece has that. Yeah. So I think for this one we don't use the kilograms. So there's another way of doing this. And if it does it say same thickness, yeah. I assume it has uniform density. So if you know it has uniform density and it has uniform thickness, right? The center of mass, there's another way to calculate it. Center of mass is the area of each piece divided by the total area. Times the point where it's at, right? Plus I guess I should write it as a sum. So the sum of, I guess I can say 1 over the total area times the sum from I to n of just A1, so AI, Ri. Right? Another way to do it. If it has uniform thickness, so same thickness, and since they're the same pieces, then you just treat it like that.
Sorry, you
We
read
can't
that
see
right
what you're
there.
writing.
Oh.
Yeah. Thank you.
Thank you. I would put the sticky note back up, but it keeps falling, so there's no point. But yeah, so there you go. So yeah, RCM is another way of doing it. So we can use that here. Let's figure out the total area. Well, the total area is just the area of all the pieces combined, right? So I guess you would treat this as negative area, right? Because you're taking it out. So do you count? No, you don't count that. So you count it as negative area. So the area of that first piece is, so I'll call this piece number 1, or I'll put it in a different color. Say that square is number 1, this square is number 2, that circle is number 3. Okay, so area 1 is just, of course, side length squared, which is 0.5 squared, which is 0.25 meters squared. Area 2 is again just side length squared, which is 1 squared, which is 1 meter squared. And area 3 is pi r squared, which is going to be, and actually negative pi r squared, because the area is negative. It's a piece being taken out, right? So it's going to be negative pi, and then r squared is 0.25 squared, so it's going to be negative pi times 0.25 squared is 16, like 0.16? No, 1 over 16 is what I was thinking of. But that's just a 0.0, running out of space, 0.0625 meters squared. Yeah, okay. So we have all our areas. The total area will just be the sum of all of it, right? So the area total is just going to be 0.25 plus 1 minus, I should write the number in the front, 0.0625 pi, right? So that's, do I have the answer still? Yes, so I have 0.25 plus 1 minus pi times, answer. And I got 1.0537 approximately meters squared. Okay, and so the center of mass will just be we have to put a coordinate system on here, right? So if I say the coordinate system is, this is 0, 0, so that's our that's our x-axis. That's our x-axis. And let's just say that's our y-axis. Right? If I could draw better, that'd be good. Okay. And so, well, guess that would be halfway. Okay, I see. So the center of mass, do we have to break it up into x and y? No, I think we can just, it's all on the y-axis pretty much. And not just pretty much, it's all on the y-axis. So the x component of the center of mass will definitely be 0, right? Because it's right in the middle. So the y component is all we really care about. So I should really call this RCMY. Is
What did you say about the x component?
well, so since I centered my axis here, right? Since I centered my axis here, it's completely symmetrical on the left side and the right side. So what that means is that the x component of the center of mass is going to be 0. It's going to be right in the middle.
Yeah.
Right.
Wait, why would it be 0? Shouldn't it be like 1 meter? Because 1
but-
meter from the bottom.
That's the y component you're thinking of.
But for the x, because it's like one's a negative, and one like direct. Sorry. If we look at it like in a plane, one would be like on the left side, the one on the right side, and it's equal, so it cancels basically.
Yeah, well, I mean, if you think of each of these things, each of like half of this object as its own piece, right? Half of this object, the center of mass of this one and the center of mass of this one would land directly in the middle. Like if you imagine like the left and right half, wherever the x component is, they'll definitely cancel. Like the net center of mass for the x value would be right in the middle.
Yeah.
Right? We don't know the y component yet. But we know the x will be right in the middle.
Okay.
Because of that's what? Sorry.
That's because it's symmetric.
Because it's symmetric. Yeah, because it's symmetric.
Okay.
Right. It's symmetric in the left and right halves, right? Across the y-axis, over the y-axis. So, I will now do 1 over the area total times. Now I'm going to need the area of each piece times its position, its y position. So, well, the y position of the circle is 0. So we can take the area of the circle, so that was A3, right? So A3, and the y position was just 0, so it's actually just going to be 0 times that, right? Plus, so it actually doesn't account into this, although it does account into that, right? So that's why it's still there. Now the y position, the area of the small square was A1, so A1, and its position is 0. So if this whole side length is 0.5, its center of mass would be right in the middle of it, right? It's a symmetrical object, and so halfway up is 0.25, right? And then finally we need the center of mass of this big one, right? So the big one is going to have a center of mass that is halfway across this, which would be 0.5. And so it's going to be A1, that's that area, and then it's going to be minus 0.5 because we're going down by 0.5. Right? So of course, this doesn't matter, right? So it's just 1 over the area total times 0.25 times A1 was 0.25 plus, well, I guess I'll just write negative minus 0.5 times area 1, which is, did I make a mistake? Yes, I called both of them area 1. This was supposed to be area 2, right? Which is just 1. Okay, and so 1 over area total was 1.0537 times 0.0625 minus 0.5. Okay, and I'll just plug that whole thing in. So 0.0625 minus 0.5 over 1.0537. 1.0537, yes. So I got a y component of negative 0.415 meters, I guess.
Yeah, I actually am not sure what you're doing here. Like, I get so you have A0 because that's a circle and it's taken out, right?
Mm-hmm.
Right?
Well, it's not 0 because it's taken out. It's 0 because its y position is 0. Look where I put the origin.
Oh yeah, sorry.
right? It's Y
But
position.
then,
Mhm.
oh yeah. No, that makes sense. Never mind. Everything makes sense now.
Okay, good.
So we can choose where to put the origin.
You can choose wherever. You can choose any place. How
So
did
I
I
can
choose?
put it at the bottom.
You can put it anywhere, and it will be you'll get the same answer. Your
So
exact
wait,
number for the Y position will change because it's you're moving your grid, but the actual like physical location of it will not change.
Yes. Okay.
why do you have for A1 0.25 if it's oh
A1 is that small square.
yeah, and it at the end of the small square is directly in line with the center of. That's
Right.
right.
Well, at
Okay.
the center of mass of the small square is going to be halfway up the small square, right? In the Y position, it's going to be halfway up. So if the whole side length, sorry, this might be confusing. The whole side length here is 0.5. So maybe that number was confusing there. Whole side length is 0.5.
Oh yeah.
So
Yeah.
halfway up is 0.25.
Yeah, because it's like right at the top, actually at the top of the right hand circumference, because like
It
the
is. It
radius
is
is
actually.
also
Yeah.
0.25.
Mm-hmm. It
Then,
is actually right there.
but then where did you count from the center of mass down towards the large one, and that's why you have negative 0.5 right here.
Yeah, because the Y component, so the center of mass of the big circle is going to be here, right? And it's negative 0.5. It goes down by 0.5.
Yeah. All right.
Right? Negative
Cool.
0.5.
Makes sense.
Yeah.
To me.
I'm just wondering, where'd you get that formula? Like, it's like the I
Areas?
haven't seen that formula. But yeah.
From the lecture. From the lecture with Springer. Here. This is it right here. Uniform
Okay, I
objects
see.
of constant thickness. You can take a screenshot if you want.
Hold up on that. I've actually never got this
Got
one.
it now, so he can cheat. He has it prepared.
There you go.
Well, other teachers are so useless sometimes.
Huh?
Tango is so useless. I'm not even lying. He doesn't even teach us anything. He goes over like the most like simplest problems in class.
Yeah.
That is just so
You must first understand the simple before you can attack God.
Someone's saying that Centroid might not be on the exam because apparently it got taken out. I'm just trying to make sure. I don't know if anyone else knows anything about it.
It's the
I
hard.
don't know. Honestly, I didn't even on the physics exam.
Sorry, Adam, could you bring that back? That was the one I didn't have.
Yes.
Hibbler 9.2 won't be on it. Does anyone know if Hibbler 9.2 is a thing?
Those are the harder centroid problems, but center of mass is still in a Serway,
yeah.
so it's gonna be on it.
Okay, got it.
Adam, I'm just confused. Why did you multiply 0.25 to the first area, the A1?
Okay.
Because that's its
Okay.
that's its Y position. The center of mass of this block has a Y component of 0.25. So we're just looking for the Y component here. That's all we're looking for, just the Y component, right? So its center of mass has a Y value. If I said 0, 0 was that red dot there, so its Y value is going to be 0.25. Right? Because we know the total 0.25, yeah. Because we know the total height is 0.5 of the whole block.
Yeah. So you just subtract it. Okay.
Yeah. There you go.
Thank you.
Okay, and then someone asked for that.
Yeah, thank you.
No problem.
So just to clear up, the reason why the area of the circle is negative is because it's like a hole, right?
Yeah, because it counts as a negative mass, kind of, right? So it's not like it's not there. It's taking away from the center of mass. It still affects it, right? But not in the inverse way that a mass would. So that's why you do it like that. Let's do maybe one more. It won't take too long. It's again center of mass from the thing. It's an iClicker question. So I thought maybe we could.
Yeah, there was also this double circle one that. I mean, if we have time.
Could you try to find it? Maybe could you try to find it?
Yeah.
And then send it to me. Yeah. So any more questions about this one? This center of mass one.
Oh wait, what was that? What Springer got as well? Like the final answer?
I don't have the final answer here. I don't know. So
yeah, that's the final answer.
Okay, good.
Okay,
there you go.
Cool.
Good.
Thank you.
Yeah, it's good to check for sure. I agree. You have to check, or it's pretty much useless if you don't check. So yeah. So any more questions about this one before I move on? Okay, take that as move on. Okay, so Oh yeah, and so I know there's some people in another chat, right? So if any of those people have questions, just say it in discussions, and hopefully if I don't see it, then someone will tell me to see it. Yes. Yes, Manuel. Yes, we can have a logic discussion. Perfect. That's what we need. I'll teach you shapes. That's kind of what we're doing right now. So.
Oh, yeah, that's true.
We're preparing. So this one here, pretty much is just find the, a rectangular sheet of metal, a material, with mass of 1 kilogram and a length of 2 meters, and a width of 1 meter, has a square cut out of it. The square hole has a side length of 0.5, and its center is a distance of 0.5 from the center of the rectangle. Okay. What is the x position of the center of mass of this object? Assume x equals 0 is at the exact center of the blue rectangle. So that's x equals 0, right? Although that doesn't really look like the exact center because of, yeah, it's kind of poorly drawn because that looks smaller than that, obviously. But look at this. This is 2. That makes 1 hole, so that must be the center if the whole thing's 2. And yeah, so find the x component. Okay, well, so we just use this formula, right? Again, he gave us the direction of our x, so that's all we need, right? So we don't really care about the y component. The y component will be 0.5, right? So r CMY is 0.5. Well, I guess if it's 0, actually, let's say that's our origin, then it's just 0. 0 meters. Okay, but what we actually care about is r CMX, right? So that's going to be 1 over the total mass times the sum of each mass from I to n. Each mass times its x position. Okay, so what's the total mass here? Well, we have a sheet of metal with 1 kilogram. Okay, we don't know the mass of that thing because they took it out. So, oh no, never mind. We do know it. Hint: the square piece which was removed has a mass of that. Okay, so we do know that. So we actually know everything now. We can do it. So the total mass, let's calculate that first. Mass is just going to be the mass of the whole thing, right? So the mass of the whole thing is 1 kilogram. I guess I'll write 1 kilogram. And then I'll subtract from that the amount of mass that was taken off, 0.125 kilograms. Okay. Then, of course, the total mass would just be what that is. So 1 minus 0.125 is 7 over 8, which is 0.875, right?
Can you move up because we can't see that part?
I always forget about that. There you go. Yeah. So good. Is that working? That's the.
Yep, that's great.
Oops, okay. So, fill in that one. So we know the total mass. Now for each piece of the mass, let's fill this formula in. So it's going to be 1 over the total mass times each piece. There's only 2 pieces, right? So the first piece, let's consider the huge square, right? The huge one, the bigger one. What's its mass? Well, its mass is 1, right? 1 times its x position. Well, its x position is 0, right? Hold on. No. I'm going to end up with oh, never mind. That makes sense. Okay, sorry. I thought we were going to end up with an answer that didn't make sense. That's correct. So its mass times its x position, okay? And then we need the other one. So the other piece here, its mass is going to be, so we're adding the negative mass, negative 0.125, times its x position. Well, its x position is 0.5, right? And I can replace m here with 0. Well, replace it with 7 over 8, right? So we're doing 8 over 7 times 1 times 0. Well, 1 times 0 is just 0, right? So 8 over 7 times negative 0.125 times 0.5. Right? And that's going to be the x position of our center of mass. So we'll just plug that in. 8 over 7 times negative 0.125 times 0.5. So I get negative 0.07, 0.071 meters. So notice our center of mass is going to be a little bit further that way, right? It's going to be like there. Well, actually, a little bit further, I think. No, that's probably about right. I thought it was 0.7, but 0.07. So yeah, and that's going to be our center of mass, and so that's the answer. And I can't tell if that's the answer. I don't have the answers here, but
Yeah, that's the answer.
I'm kind of confused about why the center of mass y is 0.
well, because I put the origin right in the center. I put the origin right here. I said the origin of my whole grid is directly in the middle of this thing. And so since I know from looking at it, like the symmetry of it, it's symmetrical up and it's symmetrical down, the center of mass, the y component, will be on this horizontal line. It'll be on that horizontal line. But that's what the x-axis is. So it's going to have a y value of 0.
Oh, okay, that's the x. Okay,
I said that green dot's the origin, right? So since I said that, then you work stuff out from there.
Can I see the total mass calculation top right, one side? What was that? Okay, so this was, yeah, that was the large mass subtracted from the smaller one, right? They gave us both of those,
the
right?
absent mass, yeah, the absent mass. I mean, yeah. So here, they gave 0.125 kilograms there, right?
Okay, cool.
Yeah.
And then we just, yeah, okay. You just simple.
Why is the 0.125, is that the mass, and why is it negative?
It's
that
mm-hmm.
Isn't 0.5 negative? Position.
Well, I'm saying this is the positive x direction. You see, I'm saying that way is the positive. So 0.5 is positive, right? 0.125 is negative because that white square is like taken out of it. It's being cut out of the piece, right? So we've lost that mass. So it's a negative mass. And it says here, hint, the square piece which was removed has a mass of 0.125.
All right.
Right? So it acts, it's not really that it's a negative mass, but it acts in the problem the opposite as mass would. So you call it a negative mass, right? Does that make sense to say it like that?
Yeah, that makes sense. Yeah.
Okay. So, okay, well, that's center of mass. I guess that's everything we got for that.
I sent you the photo.
Oh, yeah. Then we have one more problem. Okay. Oops. Sometimes it doesn't let me do what I want. Take that. Okay. So, stamped out disk problem. Find the center of mass of a uniform metal plate P obtained by removing a disk D of radius R from a uniform circular plate C of radius 2R. Okay. I see. Well, we can do this by, we don't know any of the masses, so we gotta do it by area, I guess. We have to do it by area. So if I say that is the origin, then the y component of the center of mass, the y component of the center of mass will be 0. So RCMY will be 0. We don't know what units, so I'll just say 0. Right, because it's symmetrical up, it's symmetrical down, so it's going to be on that line, and since that's the x-axis, it's going to have a y value of 0. Okay? So now all we care about is our x position, right? Our x value of our center of mass. So we're going to have to go with areas again, right? Because we don't know any of the mass values. So it is a uniform circular plate, so it's uniform. I assume that means it's uniformly thick, it's uniform density, all that. So that means we can use this formula, right? Which is RCMX is 1 over the total area times the sum from I to N of MI RCMX. Okay, well, what's our total area? Well, it's the area of the two pieces put together. So area total. Total. I guess I'll say TOT. So, I'm going to say total. So the area of the big piece, let's say, is going to be pi r squared, right? So pi r squared. Now, what's the radius? The radius this is 2r. Okay, so pi 2r squared, right? Which is 4 pi r squared. Okay. Oh, sorry. That's just the area of the first piece. Then we need to subtract. So I guess I'll say that's the area of 1. This big piece here. Okay, the big piece is piece number 1. This piece is piece number 2. Oh, it's actually there. We have letters already, P and D. So I will say this is the area of P. And then, so that is 4 pi r squared. The area of D is going to be pi r squared again, and r is just r. So it's just going to be pi r squared. So the total area is going to be 4 pi r squared minus pi r squared. Okay. Yeah, actually we can. Yeah, let's factor out the pi r squared. Right? So it's if I factor out the pi r squared, it's going to be 4 minus 1. Right? Oh, actually, I could have just combined them. What am I talking about? So, yeah. Sorry, they didn't look. My brain was not telling me that these were the same variables here. Okay. So yes, never mind. I can just. It's just 4 minus 1, so it's 3 pi r squared. That's all it is. Okay, so that's the total area. So if I do now 1 over the total area, 3 pi r squared. Okay. And I'm going to sum together all these pieces. So oh, we don't actually know the mass. Sorry. So it's not the mass. It's going to be the area of I, right? The area of I times RCM xi. So the area of the first one, or area of P, right? So the area of P is, the area of P is 4 pi r squared. And I want to multiply that by its x position. Well, its x position is 0. Okay. Then I'm going to add the area of the second one. The area of the second one is going to be negative, though, right? So I should actually put a negative there, right? It's going to be negative pi r squared times its x position. Well, its x position is r. Right? Its x position is r. And actually, it's negative r. Yeah, it's negative r.
Yeah, because you can get a positive.
Right, because you're going this way. You're going in. This is the positive x direction. So you're going the wrong way. And also think about it like we want our center of mass is going to be like here somewhere, right? So this should be a positive number. We should get a positive number out of this, right? So this is just, of course, this cancels. Okay, so it's just going to be pi r cubed over 3 pi r squared. Right? Well, the pi's cancel, and the 2 of the r's cancel, so it's just r over 3.
Yeah, scroll up for a second, please.
Sorry, but why the area on pi r2, the second one, is negative?
Because this circle is taken out of the big one. They like stamped it out. Oh. They cut it out of the big one.
Okay.
So it acts as negative area. Yeah.
Thank you.
No problem.
Center of the x position is literally the radius, right? The center of the circle.
Right, the center of the circle. Negative though, right? I mean, it's in the negative direction. So you got to say negative.
Yeah, so that's why that's gonna be negative r. Makes sense.
Right, and so r over 3 this direction, whatever that radius is. So okay, so r is like, if that's r, then r over 3 is like right there. So that's our center of mass.
Yeah.
That's the center of mass there.
I don't know. I feel like something like that's gonna come this one specifically. That's fine.
Could. No problem.
Okay. I think we should move on. We spent a lot of time on center of mass.
Yeah. Well, it's well, yeah. I guess it's not that important compared to the next stuff, but still, it'll be on the test, so better know it. Let's see here. Oh, someone did send another center of mass question. Maybe let's move on, and then maybe at the end I'll do this one, the one that Ronak sent me. Is that all right? And then we'll
yeah, that's fine.
Okay. So the next part is Yeah, let me find that. So we'll go to like the practice questions in the textbook. That's where I'm going to start the next sections, right? So suggested practice problems. Chapter 10, so rotation of a rigid object. Okay. So we start at question number 4, and this is probably where we start to struggle a little bit. So let's take a look and see if we can figure it out. So chapter 10, question 4. Okay. Okay. I'll write here. This is where we start chapter 10. So a machine part rotates at an angular speed of 0.06 radians per second. Its speed is then increased by 2.2 increased to 2.2 radians per second at an angular acceleration of that. Find the angle through which the part rotates before reaching its final speed. If both the initial and final angular speeds are doubled, and I didn't read that properly. If both the initial and the final angular speeds are doubled and angular acceleration remains the same, by what factor is the angular displacement changed? Okay, so let's start with part A. Okay, of course. So we're finding the angle through which the part rotates before reaching its final speed. In other words, we're looking for delta theta, right? What do we know? We know omega I, right? The initial angular speed is 0.06 per second, right? Okay, I'll say radians per second. Radians per second. Radian isn't really a unit, so you don't really say radians per second, but it's fine. Then its speed is increased to 2.2 radians per second, so omega final is 2.2 radians per second. And its acceleration, angular acceleration, so that acceleration, is 0.7 radians squared per second, or radian per second squared, sorry. And I wrote the wrong letter. Okay. And we're looking for delta theta. So we could just use our kinematics equations. We don't know anything about time, but we can use this equation, right? So we can use omega f squared equals omega I squared plus 2 times alpha delta theta, which is the same thing as what we had before in kinematics. Vf squared equals vi squared plus 2 acceleration delta r, or whatever the thing is. Right? So that's the same kinematics equation. It's just with angular stuff now. So we know all this. We can just rearrange for delta theta. So if I have, I'll just rearrange it first. So it's omega f squared minus omega I squared over 2 alpha equals delta theta. And let's just plug in our information. So minus something else squared 2 times something. Okay. So omega f is 2.2. Omega I is 0.06, and it's 2 times the acceleration. So the acceleration is 0.7. So delta theta is approximately 3.45. That's fine. 3.45. 3.45 radians. That's all. Okay, I guess I'll say radians. Let's see if that's the answer. 3.4, yeah, 3.5. Okay, and so that's the answer for part A. Okay, that's answer for part A. Part B, if both the initial and the final angular speeds are doubled and the angular acceleration remains the same, by what factor is the angular displacement changed? Why? So pretty much all we're saying is that I take this equation. Let's say we didn't know what WF, WI was. Let's just say it's ended up being 2 times WF minus 2 times WI squared over 2 acceleration to alpha or whatever. Yeah, alpha, that's the word I'm trying to say. Times delta theta. And so what we get out of this is if I apply the square, right? It's going to be 4 omega f minus 4 omega I squared. Sorry, the squared is just on the f on the omegas now. So it's 2 alpha equals delta theta. And so you notice, well, I can just factor out the 4 to the front, and so you can just see it's going to be 4 times as big. Omega squared over 2 that. You see it'll be 4 times as big if we left the omega the same.
Yeah, wouldn't you just say it's by 2 then? Because you're gonna just like, couldn't you factor in 2 as well?
From where? From the bottom?
Yeah.
But the thing is that that's just part of the equation. That's just part of this formula for finding acceleration. So sure, technically, yes, this does cancel. But what we're trying to show is that this quantity was the original. This right here, with the 2 in the bottom, was the original.
Okay, yeah, so it's actually by
theta.
4.
So you see it increases by 4 because we're multiplying by 4. That's the new delta theta.
Even though technically it's doubled, it actually increased by 4.
Well, it's not really that it doubled. This quantity with the 2, right, is a separate thing. That quantity is the original delta theta, right?
Yeah,
so we can literally replace it. We can literally replace it with 4 times delta theta original equals delta theta new.
Yeah.
Right? So, wow, that looked messy. Let me write that again. But yeah, that's the idea. So 4 times delta theta original equals delta theta new. So the answer is 4 times. Okay. Any questions? Okay, we're good. So I will move on to the next question, which is number 5, right after it. Here we go. So a dentist drill starts from rest. After that many seconds of constant angular acceleration, it turns at that rate. Find the drill's angular acceleration. Determine the angle in radians through which the drill rotates during this period. Okay. Omega I is 0 radians per second, right? Omega F, no, we don't know omega F, but we know delta T is 3.2 seconds. Okay. We know alpha is constant, which isn't, like, it's almost always going to be constant, really. Well, kind of. So we don't have to, that's like that important to write down, but just something that's good. And then it turns at a rate of that many revolutions per minute. Okay, so we know kind of omega F. So just like speed F or kind of omega F equals 2.51 times 10 to the 4 revolutions per minute, right? Well, actually, I think we can just say omega F equals that, right? It's not actually in radians per second, though, right? So we first need to turn, first we need to turn this into radians per second. So how do I turn, so I'll write over here, 2.51 times 10 to the 4 revolutions per minute into radians per second. So first, let's get rid of the minute. So I'm going to put a minute on the top. In 1 minute, there's 60 seconds, okay? And then I want to get rid of revolutions. In 1 revolution, there's 2 pi radians, right? So minutes, revolution. So we'll have radians per second after this, right? So it's going to be 2.51 times 10 to the 4. 2.51 times 10 to the 4. Put that in brackets. Times 2 pi over 60. So I get 2,510 over 3 pi, which is approximately equal to, two double equal signs, 2,628.5 radians per second. Sorry, this is also radians per second. Okay, so that's actually our omega F, So now we know omega I, we know omega f, we know delta t. What are we looking for? We're looking for the acceleration. So we can just use our basic, one of our basic kinematics equations, right? So we're just going to say omega f equals omega I plus alpha t, right? Which is the same thing as vf equals vi plus acceleration times time, right? So for constant acceleration. And so we know it's constant acceleration, right? That's why it was important. So let's solve for acceleration. So it's going to be pretty much delta omega over t. Use acceleration, which makes sense. That's actually I could have just gone for the definition of average acceleration, right? So this is going to be the final WF, so 2,628.5 minus omega I, which was 0, over t, which was 3.2. Right? And so that is, let me take a sip of my water and then. Did I have that still? Yeah. So answer divided by 3.2. So I got, well, exactly, 821.4 radians per second squared. Okay. Very thirsty for me. Okay. So that is the answer for A. So we found the acceleration. It'd be good if someone could check the answers as I'm going. Are they here? No, there's no answer on the page here. But yeah, if someone could check the answer for 5, much appreciated. For 5A. So I got 821.4 radians per second squared. And then we also need the angle in radians through which the drill rotates during this period. So we're essentially just looking for delta theta. And we can do this.
Question.
Mm-hmm.
How did it, for dimension analysis, how does it second square? Oh,
Okay,
no,
so
mind. From radians per second and second. Okay, makes sense.
Radians per
My bad,
second
sorry.
over second. Don't worry.
Yep.
Yeah, good. No, it's good to think about, for sure. It's always good to think about if your dimensions work out. I really should be writing dimensions in here. My writing just gets a little bit too cluttered with that, but I really should be. And so I kind of just think about it as I'm going. Is it going to make sense? But yeah, for sure. It's good to write it. So part B. Do I know the alphabet? I guess not. Determine the angle in radians through which the drill rotates. So we're going to use our delta theta. So we can use any of the, not any, but either two of the kinematic equations. So let's use just this one. So we'll say the one we used before. Omega f squared equals omega I squared plus 2 alpha delta theta. So let's find our delta theta. That's what we're looking for, right? So I can say omega f squared. Omega I squared was 0. So we can actually just forget about it. Over 2 alpha equals delta theta. Oops. There. Okay, equals delta theta. And so let's just plug that in. Omega f squared, so we said omega f was 2,628.5. 2,628.5 squared over 2 times alpha. And we said alpha was 821.4. Okay, so we'll do 2,628.5 squared over 2 times answer. Yep. So I got a delta theta of 4,205.7 radians. And there's your answer. So any questions about this question? And also, could someone check the answers in the textbook? Maybe I should.
Yeah, they're correct.
They're correct? Okay, thank you.
Someone in the chat was asking if you could do WebAssign questions, especially from the last one that we had.
Sure, that's all rotation. Yeah, that's all angular stuff, right? It's all like rotation stuff. Let's see.
That's like after this, right?
All of the Webasine questions are textbook questions, like they're from the textbook. So if you do a textbook question, then you're probably gonna cover a lot of Webasine questions.
Yeah, I kind of planned on first doing the textbook questions, because like that's like I like seeing suggested practice problems from the professor because I feel like that's the good stuff. Of course, WebAssign is also going to be the good stuff for the final exam. So yeah, so let's how about I'll do a few more of these textbook questions. We'll take our 15-minute break in about 10 minutes. Okay, we'll do maybe 2 more questions. And then right after the break, I'll do a couple WebAssign, and then we'll keep going with the textbook questions, stuff like that. Okay, so that's...
Could you go over part A? I was in the washroom for a bit.
Okay, sure, sounds good. So number 5, part A, we were just looking for the angular acceleration. So all we did is we used this formula, right? This formula. So we have to figure out what we know. So we're looking for angular acceleration. That's our goal. So we know delta t. They gave us that in the question. We know wi. Gave us that in the question. Wf we kind of knew. We just had to do a little work with the units, right? So we knew that Wf was going to be 2.51 times 10 to the 4 revolutions per minute. So I just had to convert that per minute to per seconds and that revolution to radians. So the conversion rate is there's 2 pi radians in 1 revolution. And there's, of course, 60 seconds in 1 minute. So I got that Wf, and I just rearranged, plugged it in. There you go.
Yeah, that makes sense.
Okay, so that was number 5. So let's look at number 9. That means the textbook scrolls so slowly. I think I can just change an option here. And then I think it scrolls normally now. No, it's still so slowly. I don't know why this one textbook, because like the resolution's different, I think, than the rest of the textbooks. Anyways. So number 9 is a discus player, a discus thrower, which we had this on the WebAssign. I'm doing number 9, right? That was the next one. Rotation of a rigid object. 4, 5, and 9. Yeah. Okay, and I will include the picture for this one. All right. So this man's packing. A discus thrower accelerates a discus from rest to a speed of 25 meters per second by whirling it through 1.25 revolutions. Assume the discus moves on an arc of a circle 1 meter in radius. Calculate the final angular speed of the discus. Determine the magnitude of the angular acceleration of the discus. Assume it to be constant. Calculate the time interval required for the discus to accelerate from rest to that. So of course, omega I equals 0. Omega f equals 25. Not omega f, sorry, meters per second. So it's actually just our VF, right? So our final speed. By whirling it through, so delta theta is 1.25 revolutions. Okay, this is meters per second. This is, well, with this nothing, it's 0. So assume the discus moves on the arc of a circle 1 meter in radius. Okay, so r of the circle is 1 meter. So calculate the final angular speed of the discus. Well, we just used the formula. The magnitude of the of v is equal to r times omega. Right? Omega is a vector too. I haven't been putting vector signs on this, have I? Is it a vector? Yeah. Well, whatever. Oh, no, I haven't been putting vector signs because omega I is not a vector. Is it a vector? Yes, it is a vector. What am I talking about? Okay, anyways, whatever. So, r times omega. So, let's use this. The magnitude of v, so we're looking for the omega f here, right? So the magnitude of vf equals r times omega f. So we're solving for that. We just, rearrange. So omega f equals vf over r, right? Which equals 25 over 1. So 25 radians per second. That's omega f. Okay. So, okay, that's that. let's look at, that's part A. Calculate the final angular speed, so that's it, 25 radians per second. Part B is determine the magnitude of the angular acceleration of the discus, assuming it to be constant. Well, we just use our formula again. We know the initial speed, we know the initial angular velocity, speed, I guess. Not velocity, yeah, I'm saying the wrong words. Initial omega I, final omega. We don't know delta t, we know delta theta, and that's all we need to know for the third equation. So WF squared equals WI squared plus 2a delta theta. And right before we do this, I'm going to convert this again. So it's 25 revolutions, 1.25 revolutions, I mean, sorry. And to convert that to radians, well, so we're converting it from revolutions to radians. In one revolution, there's 2 pi radians. Right? So that's going to be 2.5 pi radians. 2.5 pi radians. Yes, that makes sense. Okay. Because 2 pi is one full rotation, so a quarter of another rotation would be 0.5. And yeah, okay, good. So we know that now. So let's rearrange this for alpha. So to rearrange this for alpha, it's going to be omega f squared minus omega I squared over 2, not over 2 alpha, over 2 delta theta equals alpha. Okay, and so we can just plug that in. So omega f squared, we said, was 25. Well, 25 squared. Minus the initial, well, initial was 0. So 0 squared. Over 2 times delta theta. We said delta theta was 2.5 pi. Okay, so that's 25 squared over 5 pi. 5 pi. 25 squared over 5 pi. So I got 39.79 radians per second squared.
Just one thing though.
Correct.
The V over R, right? It's meters per second over what again? Because R is in what?
R is in the radians? R is in the radius? Sorry, radius?
Yeah, it's in meters, right?
1 meter, yeah.
And the velocity is also in meters, right?
So you're saying to get this unit here?
Yeah, how did you get the rads per
So
second?
let's take a look here. So this is VF is going to be in meters per second, right? Per meter. That's the R on the bottom, right?
Yeah.
And that's the velocity. So this is just going to be equal per second, right?
Yeah.
One per second. Radian is not actually a unit. You don't count radians, right?
Okay, that's fine.
It's just we just write it so that it makes, because it would be really weird to write 25 per second, right? But radian is not actually a unit, so it doesn't actually count. So this is the same thing, still per second.
Okay, yeah, all right. Thanks.
Where did the 2.5 pi come from?
2.5 pi came from converting the 1.25 revolutions to radians.
Oh, okay.
Right, that's 2.5 pi radians. Yeah. Okay, so
where'd you get the velocity equation from? Like
this
V equals R.
for every angular quantity, right? So every angular quantity. So if we have any acceleration, position, anything like that, it's related to the linear quantity by R. So if I want to get, if I know like the tangential acceleration and I want out the rotational acceleration, the angular acceleration, I just multiply by R. If I know the actual velocity, the linear velocity, and I want the omega, I multiply by R. Similar to position, if I know the the position, well, R is a bad one to use there, but like if I know the position of it, relative to like the whole system, like the whole thing, the question, and I want the theta of it, I just multiply by R, right? So all those things are just together by a factor of R. So yeah. Okay, so then that was our alpha. So determine the magnitude of the acceleration. Yep, calculate the time interval required for the discus to accelerate from rest to 25 meters per second. So just calculate delta t. Okay, so we can just use our normal formula here, right? So our one of our kinematics ones. So this is for part C, and this is for part B. So for part C, WF equals WI plus alpha t, or I'll say delta t. So we're solving for delta t. So it's going to be delta omega over alpha equals delta t, right? Delta t. So delta omega is going to be 25 minus 0 over acceleration was 39.79, right? Equals, so just 25 over 39.79. So I got 0.628 seconds.
I have a question. Isn't C asking for the acceleration like linear? It's finding the time, right? But it's finding the times in terms of linear of velocity and acceleration. So wouldn't we use the regular one and
Oh,
convert?
you're right. Yeah, hold on. The velocity is 25 meters per second.
Yeah, because it doesn't say radians. If you said radians, then I would have done the same thing.
You're right. So then what we do, I'm pretty sure, is we just calculate it in terms of the
we do VF.
Well, it's actually the same thing. Well, it's actually the same thing in this case, right?
It's the same thing. Yeah, but like the only thing is that you have to convert your angular acceleration to like regular or not regular. What is it?
No,
like
it's
linear.
It's linear acceleration. Yeah.
Yeah,
That's
what
true.
happens that this case is both 25 and 0.
So then that's how you would find it.
Yeah, it's like a different.
Well, the acceleration will be different. Yeah. So the thing is that, well, actually, since the radius is 1, we won't have much trouble. But the thing is that what I did is I said omega f is 25 meters per second, but that can't be right. Omega is not in meters per second. Omega is in radians per second, right? So I'm doing a different thing entirely. So what we really need to do here is just use our linear equations, because it told us that what is delta t to get to VF equals, well, VF, magnitude of VF equals 25 meters per second. So I need to use this equation. I need to use VF equals VI plus, plus acceleration t.
But what did works, right? Because we converted omega f, like we converted VF to omega f in part A, right?
And
So
it was
that's
the
what
same
you
number. And it was the same number.
Yeah.
But that's only,
Yeah.
I think if it wasn't the same number, we would have trouble here. We would be in trouble right now, right? Because, and that's only the same number because the radius is 1. So let's do it properly. So this is VF, so this would be delta V, right? But of course, VI is still 0, so we're okay with that. Acceleration over t. Linear acceleration over t, right? So delta V, okay, that's still 25 minus 0. Linear acceleration is going to be different, though, right? Well, it's not actually going to be different. So we relate linear acceleration, right, tangential acceleration, to alpha by the factor of r, right? Well, so if I want to solve for this, this would just be 1 times alpha, or 1 meter times radians per second. So 39.79 radians per second squared. So we get meters per second squared, right? And that is the number I would put in here, right? And so the number is the same. We didn't actually, the answer is the same, but that's just because r is 1 in this case. The radius is 1. If the radius wasn't 1, we would have different angular and linear quantities. They would be different numbers, right? It was just that since r is 1, they're the same number. So yeah, that's that. So good. Yeah, that's number 9. Okay, guys, so let's take our 10, maybe 10-minute break. Let's just take a 10-minute break. And I will continue after that. Maybe I'll do some of the WebAssign problems right after. And yeah.
Could you explain that?
Alright, go ahead.
You want me to go? You can go, it's fine.
Alright, Adam, you still there?
I'm here.
Okay, So what I was thinking was if you could do some like 1-part questions, because usually they never give parts in the test. Like they always just give one giant question and
That's
have
true.
one answer box. So
That's true.
if you could like find one that has like multiple concepts put together or something like that.
The thing
That would
is
be
that also the parts that we do, any one part of that could be one question. I mean, it depends on how difficult they're trying to make the test, right? But any one part of this could be one of the questions.
That's true, but like, I think like those questions. I think like in the last exam where we had like spring constant coupled with what was it? There was something else. I think like static friction, and you had to like it's like two different concepts, but it's one answer.
Yeah,
Like,
yeah. Okay, so I'll look through the textbook questions. I mean, yeah, we don't have to do every single textbook question. We can do whatever, right? So maybe also while over the break, maybe some, you guys look at the textbook questions part of if you want to see what the suggested ones are. Maybe look through these ones. From,
All right.
From these, and just tell me what you.
I've actually never used the textbook, so I actually don't know.
Or from WebAssign too. So if you get, whatever questions you guys organize, yeah, for sure, send them my way, and I will give them a try. Okay.
All right.
Okay, so 10-minute break, and I will be back in 10 minutes because that's how time works.
My God, he's got a whole ass scene on OBS. Goddamn.
Do you look at that transition though? That's actually not.
Yeah. So I will be back at 11:51.
Yo, quick, while he's gone, everybody tell me all the disciplines. I need them. It's chemical, computer, mechanical, civil, aero.
Start from alphabetical, man. Aero, then.
Wait, why do you need all the thingies? What's going on?
And next,
What?
industrial.
Tell us your secrets. What's happening?
Autonomous, the chemical admin. Basically.
Nice.
No,
Nice.
because some are combined.
Oh, I don't know if we're gonna combine them. Oh wait, actually, we
No,
probably
because mechanical, industrial have the same. Computer, electrical have the same.
Okay, wait.
As well.
Yeah, you're right. Actually, computer and electrical have like one difference, I think. Maybe not.
Even
I don't even know if they have a difference.
What do you call mechanical and industrial together?
MECU.
Like you?
You just call them by their thingies.
They're like faculty. I think it's biomedical, computer, and.
Well, I mean, biomedical is under ECE, but that doesn't really count because they have different courses.
Civils paired arrows alone, I think.
Alone, yeah.
Chemicals alone. Oh no, is chemical? No, biomed is with chemical,
It's with
right?
ECE.
Oh, biomed.
No, biomed is ECE.
Biomed is with EC, ECEB, right?
It's biomedical and computer.
ECEB, MECU, civil, aero, and chemical.
Yeah.
That's it, right?
Anybody?
Huh?
Are we forgetting anybody?
I don't think so.
Well, I mean, there's a lot of courses that are like, so I know aerospace, mechanical, and industrial.
Each admin will have to figure out.
Yeah.
Anmo, you gotta look at the schedules and see what everyone has. For you, it's easy because it's just chemical, so everyone's gonna have the same shit.
Mm-hmm.
And I have my schedule right here. I can tell you right now. But yeah.
It's because you're gonna have to make channels in the future.
Okay, we'll worry about that after physics. My brain is not working.
Yeah, this is not. I don't know why you're doing this now, bro. Listen.
I'm just setting up the roles so I can, so I don't forget them.
I just want to sleep for like 12 hours.
I slept a lot actually.
Yeah, I mean I went to sleep at 2, but I slept 8 hours, so you know.
Yeah, 8 hours is like perfect. I don't even want that.
Common sense.
What?
That's about it.
Yeah.
I'm gonna have some chai. Anyone else having some chai right now?
No, I'm having coffee. I cannot drink chai.
Really?
Just overflow.
Chai on top, honestly.
Lavender chai.
What? No. Please don't.
What? I came up at the wrong time.
Just Shy on top. That's all you need to know.
Nice.
Cop on top.
What?
Why are you streaming Minecraft?
It's because he's Musta, bro. You
Wait,
can't. He's
I want
unpredictable.
to see.
I'm
Wait,
keeping
let's
my
see.
spot in the stream.
Oh, this guy's lagging hard time. Oh.
Oh yeah, never mind. I'm not clicking on Musta's stream. I want to kind of keep my spot and I don't see it.
Yeah, I'm keeping my spot. Y'all gonna lose your spots and shit,
Yeah,
bro.
screw that.
Oh yeah, you're actually so smart for that. You're a big brainer.
Genius
Very
move.
big.
I'm not big brain. I'm just average brain.
I forgot. I'm big
Fuck.
brainer. You're right.
Plus, I ain't gonna go to a stream that's lagging heavy, bro. Like, yo, you just said
Why
a
is it
lot
so
of
lag-
time.
Why is it so laggy though?
Must have got that bad Wi-Fi. What are you doing with Bell? He got Bell.
Yes,
Must have unmute. Must have unmute, bro.
Honestly, Musta, you're talking so much smack on chat. There you go.
That's all 1v1 right now.
Are you know, we have studying today. I can't do that.
I'm pretty sure Vishal would wipe you. I got my money on Vishal. I
The
got my
thing is,
money on Vishal on
Oh,
the
actually, you're putting money on Vishal. Okay, I'll put my money on Vishal.
Hey, bro. You know what will happen? If you win, I'll give you all my credits in casino.
Vishal,
Bro, chill, we're not-
lost with level.
I'll bet 5 cents on Vishal.
Nah. You gotta bet your casino money, fam.
Bro, this is
Yo,
unfair.
if you're
Bro, I can't do it.
if you're
like
not
that.
all in, then you're not betting, fam. You're not betting right. Trust me.
Vishal, if you lose, I'll get rid of your wealthy roll.
You must be out of your
Oh.
mind. You must be out of your mind, bro. That's some insane threats.
Yo, they should definitely take away his wealthy role. Guy's been abusing it.
I'm sorry, who just said that?
Lol, that polite.
Yo, I swear it was Musta, bro. Yo, Musta, shut up, dog.
Bro, why are you talking up so much? Like, do you even have wealth? You don't even have wealth. Like, stop talking.
All right, guys, let's keep it friendly.
Nice
all right?
one, Musta. You fucking suck.
Bro, I'm lagging.
Honestly, bro.
Nah,
That's
excuses.
horrible.
Did you not see the lag back, you cunt?
Nah, you're shit.
1v1 right now.
No.
Yo, no one wants to smoke from Musta, bro.
Man's
No
gonna
one
pull
wants
out
to
like a
smoke.
360 no scope fucking jump shot.
That'd be so funny.
What the hell? They got beds?
It's called Bed Wars, bud. Of course.
No,
Are you
like
playing Bed Wars?
what do you call it?
Oh, why?
Hammock.
What
No,
is
not a
that?
hammock.
Oh,
Yo, whoever has their Discord on, can you please mute your shit, bro? It is
Oh,
I think it's
annoying.
Musta. I think it's Musta.
Yo, Miska Muska Musta.
Lucy, you're not popular, bro, by having all those Discord notifications.
He's probably
What if I
messaging
still
himself.
haven't muted
He's
Musta?
messaging
What if I
low
still
key. He's
muted him?
messaging himself to get those notifications, bro.
I don't know what you're talking about.
Yo, is it 2 FPS for everyone?
I'm not even watching the Minecraft thing.
Bro,
Game
this is
2 is
some
kind of
insane lag. Insane lag. Okay, guys, it's 11:51. Everyone mute your mics and listen to the god Adam himself.
Jeez.
He's not even back.
What a statement.
Let Adam be, bro. He's probably getting some water.
I'm sorry, whoever
Leave
said that.
him
I don't
be.
appreciate your disrespect.
Shut up, it's Vishal.
How
It's
dare you?
disrespect, okay?
How
So
dare
nice
you?
it, bro. Nice
How
it.
dare
I
you?
can't tell who's talking. Wait, is it Edsel talking? I can't tell who's talking. Or is that Ronak?
Nah,
I
it's
can't.
Edzo.
Okay.
Hello?
Yeah.
Honestly,
Hello.
let's see morale
Can
of
y'all
people.
hear me? This is a tutorial clone.
Hi everybody,
Baba
I'm back.
Booey.
Welcome back. Welcome back.
I'm back.
Baba Booey.
I hope my headphones don't die in the middle of this because I don't know where the cord is. So if they die, we might have to take another few minute break for them. They charge very fast, so like literally 5 minutes they would be at like 50% and they would last the rest of the time. So.
You can go and find it from now first, so you don't have to.
I tried to find it. I tried to find it yesterday. I couldn't find it. I don't think I'm gonna find. I mean, I'll look around here quickly. It might be in here, but yeah. So if my headphones die, unless maybe, how about we take 5 minutes right now? I'll let them charge for 5 minutes, and then we won't have to worry about it. Does that sound?
I'll take the 5 minutes right now.
Okay,
Yeah,
let's take
sure.
I should have. I know I should have charged it over just this 10 minutes. I just forgot to. So let's take 5 minutes now.
No, don't worry.
Okay, so I get like let's keep the break going, I guess, till
American.
50.
I'm American.
Well, yeah, okay, 58. Okay, well, let's just say till noon. Whatever. There you go. Okay, and then we'll keep going. We'll do some webassign right after. Okay, so I'll talk to you guys in just a little bit.
Making us wait like this is a bannable offense.
What is?
I don't understand. You're not even mod.
How
He's
dare you?
CFO, bro. He's CFO.
You assigned yourself a role that isn't even applicable. Like, there's no server CFO, bro.
Well, there is now, okay, and that's me. So.
What things do you have?
Man's
What
got
perms?
demoted so
You don't Yeah, I mean,
It's so
maybe
gay.
it's
It's
the
like it
teachers.
literally just raped us. Like literally, like get the fucking asymptotes of e to the power 2x squared and some next shit.
Okay, hi
Fucking
guys, I'm
savage.
back. Hey guys.
Hey.
Hi, Beth. Sorry, I'll go now.
There we go. Hi. I'm here. Beautiful transition. Also, there's people
Hello,
here now
Adam.
who are fixing the vent, so you might hear construction noises for a bit.
Beautiful.
Probably for the rest of the recording, but yeah. Okay. So I think we're good. Okay. So any suggestions for problems to do?
Well, there are those overview questions. Some of them are alright, but that's kind of a stretch.
What's the overview
The
questions?
overview, you know, like the lab questions that we never did. I don't know.
I don't know those ones, but yeah, if you want me to
Tutorial
take a look, I can take a look. I don't really pay attention to tutorial questions. I just do the quizzes at the end, so yeah.
Yeah, I just do them. I've never really looked at all of them unless I get stuck.
Yeah. Okay, so, well, we can do that. Well, I kind of want to move on from center of mass question. I was gonna say.
Although I think the textbook questions are better.
Yeah. So what should we do? I said before I was gonna do some WebAssign questions now on Angular stuff. But
So
like,
like I said, all the WebAssign questions are from the textbook, so I
how
think we
about
should
this?
just do.
Let me quickly make a poll. Okay, I'll make a poll.
Not even that serious, bro.
No, I know, but like we have enough people here. Let's make a poll quickly. What should I do? It'll take 2 seconds. What should I do?
What topic are you aiming to cover right now in the next hour?
Well, I'm just gonna go. I mean, essentially, I'm just gonna go in order now. I'm just gonna do the kinematics, Angular kinematics, and stuff like that, right? But what should I do it from? What should I do? WebAssign or textbook? Create poll.
I don't know. But like I saw someone say that 9.2 and 4 and 5 is that chapter 4 or 9.4 and 9.5? That's what's kind of confusing me. Someone posted in the group that we're not getting those points.
Wait, sorry, what?
Someone posted we're not getting 9.2 and then they said comma 4, comma 5. Is that chapter 4 or
Yeah,
9?
that's only in Hibbler though. Only in Hibbler. Those are the challenging questions.
Okay.
That's all that means.
Okay.
What does that mean?
So here, people can vote. Well, I guess I shouldn't show the screen actually, because the people vote what they think. Okay.
I'm not gonna lie though. I think we should do textbook because most of the WebAssign derives from the textbook.
I
so
agree.
why
I would say
not just get it from
I
the
would
source?
say textbook.
I think someone made that point earlier.
Show results.
That's true.
I'll give it like a little bit more time, but yeah. And then I'll show what's winning in like a few
Are
seconds.
you actually doing a poll right now?
Yeah, there's the polls in the discussion. Go to discussion. There's a link for the poll. Okay, I'll show the results now.
Okay.
That's what it looks like. Looks like we're gonna do some textbook because I mean it's pretty close, but yeah, looks like I'm gonna go with textbook. And how many people voted? 33 people voted. So great. Okay, so let's continue with textbook. I guess let's just go in order. I need from here. So next one would be we did 9 just now. So 11, I guess. Let's look at 11. 11 is here. So this one. Here you go. So number 11 is a car accelerates uniformly from rest and reaches a speed of that in that many seconds. Assume the diameter of a tire is that. Find the number of revolutions the tire makes during this motion, assuming that no slipping occurs. Oh, okay. What is the final angular speed of the tire in revolutions per second? Okay, so uniform acceleration from rest. Okay, so vi equals 0. Omega I equals 0. Reaches a speed of 22 meters per second in 9 seconds. Okay, so 22 VF equals 22 meters per second. Delta T equals 9 seconds, or 9 seconds. Okay. The diameter of a tire, so diameter is 58 centimeters, or I'll say 0.58 meters. So radius is 0.23, 24, 29, 0.29 meters. Right? So find the number of revolutions the tire makes during this motion. So we essentially need to find delta theta, okay, what the angle changes of the tire, right? And then from that we can find the revolutions. Yeah, that makes sense. So let's find delta theta. Can we just go right to finding delta theta? We know we can find the final, so V equals R omega. So I can find omega F by just dividing by R, right? So 22 over 0.29 equals 0.29, yeah, 0.29. So I get omega F of 75.9 radians per second. Okay. So now we know omega F, so I'll leave that here. That's fine. Delta T we know, so let's look at our equation. We're searching for delta theta, so I can use, we don't know acceleration either, so I have to use, I have to use this one. So delta, I'll use the right leg. So theta F equals theta I plus omega I T, say delta T, plus 1/2 alpha T squared. Okay. And so I can move, I'm looking for delta theta, so I can just move delta theta over here. Delta theta equals omega I is 0, right? So it's just 1/2 alpha T squared. I should say delta T squared. We also don't, hold on, we don't know acceleration. What am I doing? We don't know acceleration. So,
I think you can find it, can't you?
What'd you say?
I think you can find acceleration, can't you?
Yeah, well, we can do, yeah. So we can take this. Do I know the final? Yep, I can find acceleration. So I can take my second equation here. So pause for a second on this, right? Yeah, pause for a second on this. So it's going to be omega F equals omega I plus alpha T, right? That's our equation. I keep saying T instead of delta T. Then I can solve for, I know everything here. Yep, I know everything here, so I can just solve for acceleration, right? So acceleration is going to be delta omega over delta T equals acceleration. So delta omega is just 75.9 over delta T is 9 seconds. So
what was A asking for again?
A is asking for is for number of revolutions of the tire during this motion. So we need to find delta theta. That's what we're really looking for. And then from that I can find revolutions.
As per second, right? Yeah.
Well,
someone sent something in the chat. They sent, I don't know if you can see, look at the equation.
Delta D equals VF plus VI over 2 delta T. That would be...
Yeah, they just used the normal velocity instead of angular velocity.
No, you need to use the angular.
You need to use the angular, yeah, because we're looking for
No, you
revolution.
don't. You can just find the total distance traveled.
That's true.
And then divide it by the tires arc
Radius.
length.
That's true.
Yeah.
That's true.
True.
Well, I'm almost pretty much almost done this, so I guess we may as well just do this.
Yeah.
But that would be a way to.
Yeah. What was the other way?
Instead of doing angular stuff, just calculate the total distance traveled, right? So you have D, and D equals R delta theta, right?
Mm-hmm.
So then from there you can find the delta theta. R we know is 0.29. Distance traveled, you can just use normal kinematics for that, right? And then
just divide.
And then just divide by R, right? Yeah, and that would be delta theta.
Just like for people who watch the recording or something.
Oh yeah. Sorry, the formula is, this is the formula for finding someone like me for today for some reason. That's the formula that was suggested for to find D. Yeah, to find D. you do this, right? The distance traveled. Divide that by r, and you'll get delta theta.
Your camera's covering it up.
Ah! I put it right in the spot where my face is there. Yes. There you go.
Or you could even do radius times the delta theta to get d.
But we don't know. We're trying to find delta theta. That's we're trying to find this. We don't know that,
Okay.
right? We're trying to find that. So to find that, we're going to take this divided by this. Right. Okay, but I'll keep going on how I was doing it. So I found the acceleration by dividing by this divided by 9. So the acceleration, angular acceleration, is 8.43 approximately. Radians per second squared. So now that I have this, I can just plug this all in here for delta theta. So maybe I'll go over here. So delta theta equals 1/2 times 8.43 times 9 squared. Okay, so 1/2 times 8.43 times 9 squared. So I got delta theta is 341.42 radians. Okay, and now I just want to convert radians to revolutions, right? And so to convert radians to revolutions, so I'll write it over here. I'll say delta theta equals 341.42 radians. I want to convert from radians to revolutions. So 1 revolution has 2 pi radians. So I just divide that answer by 2 pi, and I get approximately 54.34 revolutions.
Oh, what was the radius?
2.9.
Okay, so that formula wouldn't work actually.
Which formula?
0.29.
Oh, 0.29. Okay, yeah.
0.29. Okay, I just said the wrong number. Sorry. Yes.
Yeah, okay, then it would work.
Okay.
But wait.
Yeah.
Okay, that's good.
Okay, so assume no. Yeah. Okay. So what is the final angular speed of the tire? Isn't that, well? That's kind of what I did. I already did that already. Isn't it? Yeah, I think so. Oh no, in revolutions per second. So this is 75.9 radians per second. So omega f equals 75.9 radians per second. So I want to convert that from radians to revolutions. So in 1 revolution, there's 2 pi radians. So I do 75.9 over 2 pi. So 12.1 revolutions per second. And that's that. Okay, so any questions about that question? Should I do it using this method instead, so people can see what that is?
No, I mean, it's not that hard. It's like 2 calculations, really.
Yeah, it is. Okay, so I'll just move on. So next one is 14. So 14 is on the next page. There we go. So this is about torque now, I guess, even though we're not in the torque section, but that's okay. So it's the force, right? So there. Find the net torque on the wheel in this figure about the axle through O. Taking A equals, where's A? Oh, that A is the radius of the inner circle, is 10 centimeters. B is 25 centimeters. Okay, so first of all, I'll just replace A equals 0.1 meters. B equals 0.25 meters. And so, okay, we need to find the net torque. So to do net torque, it's the sum of the torques, right? The sum of the torques. So that's what we're figuring out, the net torque, right? And that's going to be equal to, well, again, the sum of the torques. So one of the torques, I'll call this one A, I'll call this one B, I'll call this one C, of course. So we're going to be torque A plus torque B plus torque C. Okay, so let's figure out each of these things separately. So torque in general, the magnitude, I guess I should say magnitude, shouldn't I? No, not necessarily. No, not magnitude. So torque, the magnitude of this torque equals R times the magnitude of the force sine theta. So the, I guess cross product? I'm forgetting which one's the sine and which one's the cos. Yeah, this is the cross product. The cross product of R and F. So R is how far away from the axle is the torque happening, is the force being applied to. Yes. How far away from the axle, right? And the axle is this thing right here, right? And F is the actual force being applied, and sine theta is the angle between these two things, right? Okay, so let's start with A. So TA is going to be, okay, so R is the distance. So this should be the distance from the axle. It looks like it's going to be A. So 0.1. I might make a mistake here, so let's see if we can get it. 0.1. The force being applied is 12 newtons. So let's write 12. And the angle between them is 90, isn't it? Why is there...
Yo, how do you have TA being 0.1 and then is this... what are you solving for TA? What are you using to the basically
the torque from this force being applied. A here. This one right there.
Okay, yeah.
So it's the distance that the force is being applied from the axle. That's A. Times the force, 12. But why like in the 30?
It would be 60 degrees. It would be 60. Because.
But I'm looking at.
You just. Right, I think 60. No, because that's not how it is.
Oh, that's not actually a right angle.
No, that's not. 60. Because I think you just draw like a 90 degree between the line they have drawn. Like
Yeah, here. But that would be 30, wouldn't it?
Between those two, it would be 60. A and the small a.
So the angle from the line that you just drew all the way to the blue force line.
Yeah.
Here to here.
Yeah.
Isn't it the angle from
O, because that's...
It should be from O, not from there.
Well,
that looks kind of awkward.
It's the angle between these two vectors. These two vectors, right?
With R being what?
R is like where the force is being applied, how far from the axle.
So that's
the lever arm.
Isn't it technically supposed to be R sine theta? Like the y component of R? Wasn't it something like that?
Yeah, it is something like that.
Yeah, I understand what you mean. I think because like I don't know if it like the blue arm, is it coming from the top of the inner circle or is it coming like right where A connects to it?
I think it's at the arrow A. Like that's how it would work, right?
It kind of looks like it should be there. Yeah, it should like it.
Yeah,
but then why would they give the other angle?
Yeah, because then that would just be 30, wouldn't? I mean, that would just be 90, wouldn't it?
Yeah.
Just that angle.
But you got the sen, because I think it's from O.
Yeah.
This
is from the axle.
This angle, like this angle. You're saying? No, not that angle.
No, that's not what I mean. I mean you just draw it from the top.
Here.
Yeah.
Yeah, like that.
Oh.
You're taking into account a lot of like non-existent like that's not where R starts from. R is from the origin to the blue line, unless we're assuming that the blue line is at that point at the top there. Not sure.
Maybe the angle between the line A and the red line that Adam drew is 30.
Yeah, that's 30. That should be 30. Yeah, that should be 30.
Wait, what's 30?
It's very hard. It's hard to draw here, but yeah, that angle is 30.
Yeah, so if we're taking into consideration that R sine theta is like the y y force of the r, like the position vector, then we're good. It's just r sine, right?
You cut out right there at the end. What did you say at the end again? It's just r sine 30. 30, that's what you said, right? Yeah. Yeah. It seems like, well, just the angle between.
Yeah, I mean, I don't think they would give you the angle like that if it was just supposed to be 90 degrees.
No, they wouldn't. They wouldn't. Yeah, for sure. So we're supposed to be using it somehow. But isn't this defined as the angle between this vector, and this vector? Isn't that what this is supposed to be?
I think
maybe that's not the position vector. Maybe
I think we're confusing that with force. It's not force, it's torque. So I think it's the y axis of the position vector.
The y component of the position vector is that. This, well, up to here, like that. Right? Which isn't the full A.
Yeah,
Assuming it touches there. A sine 30? A sine 30? But we don't. Oh, yeah, A sine. Oh, okay. So
Look
R
at
would
it
be.
this way.
Mhm.
No, it is 30.
If you put
move the position vector tip to tail with or tail to tail, sorry, with the force vector,
Then it'd be 90.
then it'll be 30. Oh, it's not 90.
Right.
Okay, look at it this way. What if you
Yeah.
moved A to be perpendicular to the radius?
Moved A.
Yeah,
to
that's
be-
what I'm doing.
It would be pointing straight left, where that dashed line is, right? So you wouldn't have sine theta. So now you move A downwards, and that's your angle.
Like you mean like rotate this whole thing so it's facing up here, right? Facing up here, so it would meet. A would be like that. Is that what you're saying?
No. Like where the dashed line is. Imagine if that was the force by A.
Okay. Yeah.
Then you would just have R times F, right?
Yeah.
But
Yeah.
when
Okay.
the small
You move A downwards. If you move A downwards, then your angle's 30.
But the angle between what and what though? The angle between the old force and the new force is 30. And the angle between the direction vector and its well, nothing, just this made up line that we made.
You want to maybe try getting TB, TC and see which one gives the right answer, sine 30,
Okay,
sine
sure.
60, or sine 90.
Well, yeah, so for this one, how far is it from the lever arm? Well, it's B away, right?
Look,
and that,
because
Mhm.
Yeah, go ahead. Okay, so what I was thinking was, if you put it like where the dashed line is, what's your angle?
My angle is 90 here.
Yeah. So sine theta would be 1. But then if you change it, then it has to either be 60 or 30. So we just have to figure out like which one it is, because you have to find like what component of sine theta would make it back to that original dashed line, I guess.
But I think what when you say that is, I think you're still assuming that the force is acting right there. Then the angle sure is 30. Then I see it's 30. If the angle was still up there, right?
I think you're right. I think the angle's 90.
Right? But since it's acting here, right? Because if it was acting here, I see it would be theta should be 30 if the force is acting there. But we've rotated the whole thing. This angle is still 90 degrees. Right? It's actually acting here. Right? Like that dotted line is just a dotted line. It's just like there's no physical force happening there or anything. Right?
That means it should be 90.
Let's try all. I mean, they all seem like they're 90. So let's try all of them at being 90.
Well, like the reason I'm saying that is like, why is a dashed line there then? Shouldn't be like where the force is acting. Like
They sometimes give you extra information just to put you off.
Let's try with them all being 90 and see if we get the right answer. If not, because they look like they're all 90. This TA, okay, sine of 90. I won't do that color.
I think your torques are wrong, by the way. It should be negative TB, negative TC.
Yeah,
Oh,
I
yeah.
just said all of them positive, but yeah. Let's figure. Then you think the direction. Okay, this one's going clockwise, so that's positive, right? And then I'll calculate that in a second. TB is going to be the magnitude, the distance from the axle, so that's b, which is 0.25, times the force, which is 10, times sine of 90, right? Sine of 90. Not 9 degrees, 90 degrees. But it's going to be a negative one because it's pushing clockwise, right? Same with TC is going to be, again, negative. It's going to be B from the axle, so 2.5. Force is 9, and it's going to be sine of 90 degrees. So I will do 0.1 times 12 times sine of 90 is just 1. Okay, so I got 0.1 times 12 times sine of 90. Yeah, 1.07. Okay. Oh, hold on. I'm in the wrong. That didn't make sense. Yeah, I realize that doesn't make sense. I'm in the wrong mode. So I'll do that again. 0.1 times 12 times sine of 90. Okay, there you go. 6 over.
Oh, okay. Adam, someone sent the solution. It is 90. It
90?
just gave it for no reason the 30 degrees.
Okay.
Yeah.
So it's just to confuse you.
Yeah, I guess so.
Dickheads.
So there you go. We got that at least. Well, they're all sine of 90, so I can just forget about the sine of 90. It's just one, right? So
Yeah, it literally says on the master it, the results, the 30-degree angle was not required for the solution since each force acted perpendicular to its lever arm.
Yeah.
Yeah, that's what I was trying to say.
You have access to mastering physics?
Yeah, everyone does. It's on just go in overview, and then you just have to go down to the specific, like questions like these are there, and then they give you it, they explain it.
Did you say mastering physics?
Are you sure you don't mean website?
I know what you meant, like, come on.
Oh.
It's a tool.
No, I was asking mastering because I knew we weren't using mastering physics this semester.
Yeah.
No, that's the website, Serway.
So I was about to say, how about being using the wrong textbook the entire time? That would be tragic.
How's a net torque negative? Or like,
well, it's in the
can it be?
negative. It's in the negative direction. It's in the negative direction.
Oh yeah, okay,
right.
never mind.
It's going clockwise. Yeah, so it's okay. Okay, that's
Do
it.
you have the actual like for this to confirm?
I think, but someone's found this answer. Let's see it here. So there's just a link someone sent me. So here. Show answer. I can't see. Click grade this question.
Oh no.
Just click it again and skip through everything.
Click grade this.
Click here to begin.
Click here to
No.
begin. Click here to begin.
Click here to begin. Yeah, and just skip through everything.
Oh, okay.
Yeah, you just keep
That'll
skipping
show you
and
all
it'll give you a solution. Oh yeah, if you read that, it says it.
Okay. Magnitude clockwise. Note this thing. 38-degree angle was not required for the solution since each force acted perpendicular to the lever arm.
Well, there we go.
There we go. Yeah. Good. Okay. So there you go. So yeah, net torque is in what units? What units are net torque?
Newton meters. It's a Newton meters.
Times meter.
not
Yeah, that
joules.
makes sense. Yeah. Newton times meters. Yeah. Okay. There you go. Okay. Well, there you go. That's that. Let's move on to the next one.
Just to be clear, what was
Yes.
B and C though?
What'd
What
you
was
say?
C actually?
The torque? The torque from C?
Yeah. Yes, it's actually. Oh, okay. So it's just like, where did 9 come from? That's the
90?
force?
Or 9, sorry, 9. 9, yeah, that's the force. That's the actual magnitude of the force. So it's the
Then-
distance from the
negative-
axle, force, sine of the angle between those two things.
So they're all, well, so B and C are both 0.25 away, right?
Yeah, they're both
Yeah.
0.25 away. One is 10 newtons, one's 9 newtons. They're both at a 90-degree angle with each other, with the direction.
Yeah, and then the other one was what? TA, 0.1, because it's
0.1.
from the
From the smaller circle.
Okay, yeah. Cool.
And 12 and then sine of 90. Okay. So next one is 14, I think. Yep, 14. So 14. Oh, we did 14. Hold on. The cat's yelling out the door. Let me just let her in.
Show the cat.
Let us see
If I
that.
can get her and she doesn't run under the bed. Come here. Okay, no, she ran under the bed, so I can't. I'm not gonna. She'll come out and I'll. When she comes out, I'll. Show her. She doesn't want to deal with physics. Okay, so.
Relatable.
Oh, actually, the answer was here. Actually, I had the answer in here. 14 negative 3.55. Is that what we got? Yes, that's what we got.
Yeah.
Okay.
Got it.
So 15 is next. Is here. So there's that. Oh, wrong page.
Wait, this is Springer.
Like this is just. What do you mean? This is Springer? Like
the person who put all these practice stuff.
Oh yeah, that's Springer. That means.
Yeah, we didn't get. I was just like, I never got these things. Wow, man.
If you wanna take a screenshot, go ahead. Take a screenshot now.
Yeah, sure. You can just like send it later. It's fine.
That's true.
Yeah.
Actually, you know what? Actually, I have them here. I sent them to someone, and I can just put them in
Like my professor.
Yeah.
That's crazy.
That's fine.
You just go to there.
There's one.
I can send it. You guys can continue.
I got it there. There you go. I sent it in discussions. It's there. Okay.
Cool.
So, 15. Okay, a grinding wheel is in the form of a uniform solid disk of that radius and that mass. It starts from rest and accelerates uniformly under the action of the constant torque of that. Torque of that the motor exerts on the wheel. Okay. How long does the wheel take to reach its final operating speed of that? Through how many revolutions does it turn while accelerating? Okay. So let's write down what we know. Okay, M equals 2 kilograms. Okay. R equals 0.07 meters. Okay. Torque is equal to 0.6 Newton meters. Okay, that's all we know. That's the only torque that's on the wheel, I assume, right? So how long does it take? So we're looking for a delta T. So since we're looking for a delta T, is it from rest? It starts from rest. Okay, so omega I equals 0. We don't know anything else. We don't know anything else about omega F. Omega I plus AT. Omega I 0. Okay. Looking for T.
Well, isn't omega F thing 12?
Oh yeah, you're right. How long? Okay, that's true. How long does the wheel take to reach its final operating speed? Very good. Omega F is 1,200 revolutions per minute. I'm going to convert that right away to radians per second, right? So it's going to be second. So in 1 minute there's 60 seconds, and in 1 revolution, radians. In 1 revolution there's 2 pi radians. Okay, so
you know that like you're gonna have to go back to revolutions afterwards. This question's kind of working in minutes and revolutions.
I guess I could keep the units. You're right.
Yeah, because then you're just working with a bigger number anyway. Well, no, never mind. That was wrong. You're working with a smaller number, but you're gonna have to convert it back anyway.
Yeah. Okay. Let's see what happens if I leave it. Okay. So, oh, my headphones just made a noise. Can someone say something? Make sure I still hear.
Hello.
Okay. Yes. Okay, we're good. Okay, they just made some noise for some reason. Sometimes they do that. So, okay, we'll leave this. This is our final speed. We know the torque, so we're probably going to say that the net torque. We don't know. Oh yeah. We know the radius. Okay, the net torque is equal to the what's that called? The inertia times the angular acceleration, right? Which is like F equals ma. The net torque here is 0.6. The inertia is mr squared. Yeah. mr squared, so the mass times the radius squared, times the acceleration. That's what we're looking for, right? We need the acceleration. Sorry, let's figure out why we need the acceleration. So I'm looking for time, so I'm going to have to use one of these equations. I can use this one. Oh no, which one can I use?
Dealing with the disk, right? The inertia is half mr squared for a disk.
The what's the
The inertia.
What's a half? Inertia is a half mr squared. Oh, okay. Yeah. Why did I say mr squared? Is that just?
That's general inertia for point mass.
Oh, okay. Oh, okay. I see. Okay, I see. Yeah, that's what I did wrong. Okay, so you said 1/2 mr squared.
Yep.
Okay, let me write that here. Yeah, the mr squared is just for point mass.
Wait, is this summation? What's that? 0.6, which is a net torque.
Net torque. Net torque is 0.6.
Torque. Okay.
Point mass.
So is that like a formula for disks? That is
Yeah, there's just a sheet that has a bunch of them, and you'll be given it on the exam about what the inertia is for different shapes, stuff like that. So that's the inertia for a disk. We're looking for the acceleration because I need to find delta t. Let's look at equations that have delta t in it. Okay, so there's two equations. There's I'll just write it like this: delta theta equals WIT plus 1/2 AT squared. Okay. And there's also WF equals WI plus AT. We don't know delta theta, right? So, and we also don't know T. So it doesn't look too good there. But what do we know here? We know WI. We know WF. We are looking for T, and we can find acceleration like this. Yeah, so we're going to use the second one. And so we can find acceleration using this formula. We know M, we know R, so we can just rearrange here. So I'll actually just leave this as T, but it's the net one. Maybe I'll say T net. So I will take this and rearrange it. So it's going to be 2 times the net torque divided by mr squared. That's equal to the acceleration. Well, I guess. Okay, anyways, I'll leave it as not a vector because it's okay. So we can solve for that here, right? We can plug that in here. Should I solve or? Yeah, maybe I'll just solve now and then we'll see what it is. Okay, so 2 times 0.6 over the mass, which we said was 2, times the radius, which we said was 0.07 squared. That's that. So the acceleration is 2 times 0.6 over, the 2's cancel, sorry, didn't see that. 2's cancel. So it's 0.6 over 0.07 squared. So I got the acceleration is 122.45 radians per second squared.
Quick question. Where did you get 1/2 in the mr squared?
Oh, it's from this. This is this one. So the inertia for a disk is 1/2 mr squared.
Oh, yeah, the list they gave, like
yes.
the chart.
Yes.
Yeah. Okay, got it.
That's
Thank
right.
you.
So I'll erase that because it's kind of in the way, but yeah, that's right. So there you go. That's our acceleration. Now I can just rearrange this one for t. So I can say delta omega over alpha equals t. So delta omega is the final minus the initial. So just 1,200 minus 0 over the acceleration. This is in radians per second. So I should turn this into radians per second. Yeah. Okay. So I got to turn this into radians per second anyways. So there you go. So revolution. Wait, is that in radians per second? Hold on. This is in.
Yeah,
it
would
is.
it be?
Because you're finding time.
Radian.
Yeah, but time is clearly in minutes or seconds on.
Newton.
What is
So
that?
what are the units on this? What are the units on it? It's Newton meters equals one half, whatever. Mass is kilograms. R is meters squared. Alpha is
That's a giveaway.
meters
That's a
per
giveaway.
second squared. Yeah, okay. So there you go.
Yeah.
Wait, actually no, hold on. I jumped the gun a little bit there. Let's do this different way. This formula here. So it's 2 doesn't matter. Newton meters over kilogram meters per second. I mean meters squared. How is that?
Yeah, you'll also have to then change Newton. Newton is like kilograms something.
Oh, yeah. Kilogram meters per second or something like that. Kilogram, isn't that kilogram?
Yeah, I'll
1
check
Newton is to move 1 kilogram 1 meter. Per second?
Kilo per second square, yeah.
Per second
'Cause
squared.
it's mass times acceleration.
Yeah, per second squared. So
kilometer
these
per-
cancel, these cancel. It's just per second squared. So radians per second squared.
Yeah.
Yeah. So that is.
But the other one's still revolutions per minute.
Yeah. So I do have to change. That there. So this will be fix that line. So in 1 revolution, there's 2 pi radians, and in 1 minute, there's 60 seconds. So I'll just squeeze that in here. So that's going to be 1,200 pi over 30. 40, which is 40 pi, which is approximately 125.66 radians per second. Okay, so then that's what this should be. So 125.66. 5.66, that's good. Over alpha, and alpha we said was 122.45, so gonna be close to 1. So answer over 122.45. So 1.026 seconds is my answer for time. And yeah, Manuel, I just saw the thing Manuel said. Yes, looks very nice not having the watermark.
What?
I used to have activate windows in the corner. Don't have activate windows anymore. I've gone up.
Oh.
Yeah, that's it. So there's our time, and that's what I was looking for, right? How long does the wheel take? Yeah, there you go. So that's the time. Through how many revolutions? Well, that we use this equation for that I wrote in the middle here. We use this equation for. I wrote in the middle just because I was trying to decide which equation to use. So let's use this one, right? So we're just solving for delta theta, right? That's what we're just solving for. Through how many revolutions does it turn? Yeah. So just to solve for delta theta, well, it's already in that position. Omega I is 0. A delta t is all we care about, right? So it's this is equal to 1/2 alpha t squared. That's what I meant to say. 1/2 alpha was 122.45 times t squared is 1.026 squared. Okay, so 1/2 times 122.45 times 1.026 squared.
That's gonna be in radians though.
Yes, that'll be in radians. So that's
Yeah, it's radians.
64.45 radians. So I want to turn that into revolutions. Revolutions. Yeah. So 64.45 radians. Convert that to revolutions. So in 1 revolution, there's 2 pi radians. And so just answer divided by 2 pi. So I got 10.26 revolutions.
Yeah.
That's the answer for that. Right, yeah. So there's that. Okay, so any questions about this question?
Nope.
No? Okay.
That was a
Can we
good
get a quick recap of like what we did?
Sure, for sure. So, question asked us, how long does the wheel take to reach its final operating speed of that? So I knew I had to find delta t, of course. So I looked at this equation here, this one of our kinematics equations, right? And so I saw, okay, well, we know omega f gives it to us here. We know omega I starts from rest, right? Starts from rest. We know, well, we don't know t. Okay, we don't know t. We don't know acceleration. But it does give me torque. It gives me net torque. And I also know that the net torque is equal to the inertia times the acceleration. So I have a way of finding the acceleration here. I know the net torque. The inertia is 1/2 mr squared. Well, I know m and I know r. Right? So I know all these things. So I can just rearrange for alpha. Okay, I did that. I did that here. Solved for alpha. Oops. Solved for alpha. And then from there, I went back to this equation here. I rearranged for t, right? Since I know alpha now. I know alpha. Rearranged for t, plugged in the values. I got that for t. So that's part A. Then for part B, I went to this equation, another kinematics equation. I'm looking for delta theta. So let me read the question first. Through how many revolutions does it turn while accelerating? So how many revolutions, that's really delta theta. That's how many times it spins, right? This is just in radians though, right? So that is equal to omega I t plus 1/2 alpha t squared. Omega I is 0, so that just cancels out. So this is just 1/2 alpha t squared. I know all these things. I know everything here. So just plug it in, and I got that many radians. I just convert radians to revolutions at the end, and that's the answer.
I have a question.
Yeah.
You said the formula for, I think it was inertia was 1/2 mr squared.
For a disk. For the inertia for a disk is 1/2.
Is that derived from somewhere, or is that just like a?
It's not on the summer sheet. Like,
It's
on the
derived
summer
from
sheet?
somewhere. Yeah, it is. There is a sheet in the formulas. It's derived from just like, I think they integrate the r. They integrate the r with respect to m. Yeah. No, that's not.
I don't
That's not true at all. No, they. You don't have to worry about that too much. Just like, it's just they will give you a sheet. Yeah.
Is it there though? Is it there? Because I don't see it on the
where?
summer sheet. The summer sheet? Did you say it's on the summer sheet?
I didn't say it was on some sheet, but maybe someone else did.
Oh, okay.
So.
Never mind.
Point mass, L point mass. I can't even remember what lecture it was in. I mean, I would assume it would be in. Well, torque. It would be in torque, wouldn't it? Let me find it.
If you check pinned on discussions, physics discussions, there's a PDF that Jasper sent. It has everything on it.
Someone just sent one too.
Yeah. And yeah, someone just sent it.
There you go. But yeah.
But if you want to look at the PDF Jasper sent, it has like all the different formula you need to use.
Oh, that's good. I like that.
So
yeah.
Yeah.
Okay, I'm gonna print that. Print.
Man's doing it right now.
Right now. Yeah. Not wasting any time. So yeah. Okay. Okay, so there you go. That's that question done. We probably have time for one more full question, right? Because then it'll be 1 o'clock and that'll be it. But we also have, remember, we have another session later today, right? At 6, I think I said, right? Or what did I say?
Also, remember we have an exam, because I keep forgetting that we have an exam today.
We have an exam in.
Yes, please go to CEN. Please go to CEN.
Yeah.
Don't fail.
Yeah. So I need to print my
We have
thing.
to start exactly at 3.
I don't know.
I
would
honestly,
recommend
no
it
idea.
so you don't worry about it. Yeah. Okay,
I was
so
gonna hold up for.
So let's keep going. Let's get another question. So that was what? We just did 15, I think. Where are we? We just did 15, I'm pretty sure. So 18, and if not 19. So 18 is here. Okay. Oh boy. Okay. So Looks like another disk problem.
Yeah.
Oh, it's here. So Discord, so you see it. Okay. So.
So I'm just wondering, where was that problem set again? Like where?
Oh, the for practice
Posted
problems, I put that in discussions, and it's pinned down in discussions.
Okay, perfect. Thank you.
Oh yeah.
Put the wrong problem by accident. There you go. Okay, so a disk. Yeah, that's true. Okay, well, someone just reminded me again. I said it at the beginning, but I'll say it again. If you're doing the CEN thing, you gotta do your academic honesty pledge for CEN. They will not mark your test. They will not mark your test if
This section of the video is sponsored by CEN.
yeah, exactly. Yeah. So for sure, make sure you do that. I did it this morning. Just printed it and signed my signature wholeheartedly that I agree. And yes, so go for that. Okay. So a disk having a moment of inertia, which is that, is free to rotate without friction, starting from rest about a fixed axis through its center. Okay, a tangential force whose magnitude can range from 0 to 50 can be applied at any distance from r is equals 0 to r equals 3 from the axis of rotation. Find F and R that cause the disk to complete 2 revolutions in 10 seconds. Okay. So we don't have to figure it out. Inertia, well, actually, this will probably help. Inertia for a disk is, we said, 1/2 mr squared. We also know which is equal to 100. Okay. Omega I is 0. Torque is equal to R. Do we know any mass here? No, we don't know any mass. R is equal to, no. Tangential force, okay, I'll just call it AT for now. AT is between 0 and 50 newtons.
Sorry, guys. Where do I find the pledge for the CN class?
Email. They email it to you.
Oh.
Yeah.
And you hand it in the CEN assignments.
Yeah, you go CEN assignments in the course shell. Yeah.
The instructions are in the email that she sent you, though.
Yes.
So
We also have an announcement, I think, or maybe it's pinned in CEN.
Yeah. Just go to announce, scroll up a little bit. He explains a lot.
Okay, so then the tangential force, not tangential acceleration. There's a force that can go from that to that. Okay, can be applied at any distance from there. So little r is between 0 and 3 meters. Because I'll put the units here just so we know what everything is. Okay, find F and R that cause the disk to do that. So we know the disk is to complete in delta t, which is 2 seconds. Okay, nope, delta t is 10 seconds, and the 2 revolutions. So I'll say delta theta equals 2 revolutions. Okay, we're trying to find what F and R have to be. So it looks like this. Let's just say this. I have a disk, moment of inertia is like a pole coming through it, right? Like that. So that's the axle. Okay, and it's spinning. So this is the R is anywhere, I guess anywhere like that. So this distance is anywhere from 0 to 3. Doesn't really make sense, but the place where you can apply the force is anywhere from 0 to 3. And the force is anywhere from 0 to 50. Yeah, anywhere from 0 to 50. So that's F, that's R. I guess actually I should not draw it like that. I should draw it like this. So that's F. But it has to be positive. Well, sorry, never mind. Sorry, it can be whatever. Okay, I'll draw this direction just so it's positive torque. But no, sorry, this is just F. Okay. So we can find R. Nope, we can't find R, but we can So we have a few equations here. Let's figure out what all our equations are. We know that 1/2 m r squared equals 100. Right? In other words, mr squared equals 200. A little easier to write like that, right? That's from this. That's saying that the inertia is that. Okay. We also know, well, what do we have to find? Pair of values F and R. Okay, so let's look at what the torque would be on this. If the sum of the torques, but there's only one torque, right? So that's just, so the sum of the torques equal the inertia times alpha, right? Yeah. Then it's just T, like just there's only one torque, so I'll just call it TA, right? Because there's only one, is inertia times that. Let's figure out what TA is. TA is the lever arm times the force times sine of the angle between them. Sine of the angle between them will be 90, so that's 1.
It's for me.
What'd you say? Sorry? Not for, what was it?
It's for my computer.
What's for, I'm confused. Okay, I'll just keep going.
I think he left it unmuted.
Oh,
Yeah,
okay.
yeah.
Okay, yeah. That's, okay.
Oh, sorry, guys.
Yeah, that's okay. So, R is anywhere between 0 and 3. So we're actually we're solving for R. I guess call it R. And F, we're also solving for F, right? We're also solving for F. And sine theta, we know theta is going to be 1, so it's RF there, right? TA is the just the tangential acceleration, right? So not the tangential acceleration, the torque. Just I said TA, and so then I was like tangential acceleration, but that's not right. But I can put that in here, and I can say RF equals IA. Okay. So now I have this formula and this formula together. I'm trying to solve for R. What do I know here? Okay, I don't know much. So I know I.
Yeah.
We can find angular acceleration.
That's what I was thinking. I was thinking the next thing would be, yeah. That makes sense. So yeah, we can find that, and then we just don't know. We don't know this. Don't know this. We don't know either of these either. Do we? No, we don't know either of
Is
those.
it I equals to 200, right? And T equals to I times angular acceleration. We're trying to find angular acceleration.
We're trying to we can find angular acceleration. That's okay. We'll figure that out with these things, with this and this. What I'm trying to figure out is I'm trying to get two equations with two unknowns, right? So and the two unknowns will be R and F, right? But the thing is that I still don't know what mass is.
I think mass cancels out.
No, you can find mass from moment of inertia, maybe.
But moment of inertia has R and M. That's what this is kind of here, right? It has R and M, and we don't know what R is either. R is what we're looking for.
Isolate it for R and plug it into this equation.
And then I will be, but we'll still have an M. We'll still have an M lingering there, right?
Oh.
Right, we'll still have an M. It's a good idea, but we'll have M lingering there. So, what am I missing? TA is that, unless this isn't quite right. Moment of inertia.
It says like if it's a unique answer, couldn't that mean like there's multiple answer combinations of R and F that equal that value? So maybe there's like more than one answer.
Because there is complete.
Than one combination.
Yeah, maybe. Find a pair of values that make that happen. Well, let's just combine them and let's see what happens. Okay, so if I, no, but nothing's gonna happen. That's the thing. So if I look here, okay, I have this equation, and I have M. What is it? mr squared equals 200. 200. Well, again, let's just make it completely clear. I know this. I'll find this next. Okay, let's just do that and see what happens. And then these are my unknowns. These are okay, and this is okay. The only thing that's not okay is this M being here. So I have to figure out a way to cancel it. Let's find the angular acceleration now, and then because I'll show like that. Let's find the angular acceleration now, and then we'll decide after what we're gonna do. So angular acceleration, we need we don't know omega f, but that's okay. We do know delta theta. We do know omega I, and we don't Oh, we're looking for acceleration. Yeah, and we know delta t. Okay, so we'll use this equation, I think. Yeah. So delta theta equals omega I t plus 1/2 alpha t squared. We said omega I t was 0, right? Yeah, omega I t was... Well, omega I is 0, so omega I t is 0. So this is just equal to... This is just equal to... Give me 2 seconds, sorry.
Cool.
He's so still, I thought he was frozen.
No, I just stopped talking for a second. Okay, I'm here. So, yeah, omega I t is 0, so then we just have 1/2 alpha t squared. So 1/2... never mind. I thought I had all the information here. So this still has to show delta t. And I'm just going to rearrange this for alpha, right? So it's going to be 2 delta theta over t squared equals alpha. I'm going to change this 2 revolutions. So we know everything here now. We know delta theta. We know t. That's all we need to know. And so we also need to convert this delta theta, which is 2 revolutions, into radians. So in 1 revolution, there's 2 pi radians, right? So the revolutions cancel. So it's just going to be 4 pi, right? So this is going to be 4 pi radians. And now I can just plug it in. So it's going to be 8 pi over, well, I'll be more clear. I'll say 2 times 4 pi over t squared, and we said t was 10. So over 10 squared equals alpha. So 8 pi over 100 is well, I'll just go right to the approximate, is 0.25 radians per second squared. Okay. So now we know alpha. We know this. It's that m that's still screwing me up. If that m wasn't there, or if somehow we could get rid of it. Now, hold on, let me think. We can get... What if we used... No, that wouldn't do anything. Am I not using some information here? A disk having a moment of inertia of that, I use that. Free to rotate without friction, starting from rest.
You can relate the probably the linear acceleration to the angular acceleration using r theta, I think, or something like that.
I would be able to if I had r. I don't have any r though, right?
But then the r's will cancel out, I think, on both sides.
I know. Yeah.
Because you'll have I times alpha, which is r theta, and then that's equal to RF.
Right? Wait, I times alpha. Oh, I times regular alpha? No.
Because alpha is equal to r theta, is it not?
Alpha.
Alpha is equal to tangential acceleration divided by r.
Yeah.
Oh,
so
okay.
Can I find the? But I don't know the tangential accelerator. That doesn't really help because I just. Oh no! Wait, I can. That does help. Wait. Okay, because I can do alpha equals AT over R.
Yeah.
I know this number. I know this number. Yeah, that doesn't really help. Or does it help? No, it doesn't really help because I still have. Yeah, actually, I don't want to get rid of the R. I was thinking this would get rid of it. No, it wouldn't actually even get rid of the R. So never mind. Because I still have this unknown. It's not like we know that. If we knew that piece of information, okay, let's look at what the pieces of information are here. A disk having moment of inertia of that. Free to rotate, starting from rest. Tangential force whose magnitude can range from that. So tangential force can be applied at any distance from that to that from the axis of rotation. Find a pair of values that cause the disk to complete that many revolutions in that many seconds.
Wait, isn't tangential force m times at? Like MAT? Mass.
Yeah, I guess so. Yeah. Some of the forces in the tangential direct. No, does that make sense? Some of the forces.
Like we already have t in the equation right now, right?
AT. Well, we can have AT if we wanted to.
Ft
Can't we
equals
just
m.
solve for
But then we have
inertia
m.
times alpha gives us torque, and then we can just substitute any values between the range for R and F, because we just need one pair, right? Does that make sense?
Oh.
Yeah,
That's
we
a
can,
number.
but like the other question asks how many like distinct values there are and stuff. So how would you do that?
But it'll
Adam, I
always.
also had a suggestion.
Yeah. Go
Can I
ahead.
go on?
Yeah.
So we know that theta is equal to S over R, right?
How is
Yeah.
Does that any help? Can it help us?
Theta. But we don't know much about the linear stuff either. I see why people want to change it to linear, but what do we know about linear? The linear quantities here, right? Like, it doesn't change.
Yeah, you're right.
Right?
You're right.
So that's the thing. It's definitely a good move to try to change to that. But there's no other piece of information. Is it?
Wait, you can find a final omega, what is it called? Angular velocity, right?
Angular velocity.
Yeah, you can find that.
I guess so.
And then,
Yeah.
Yeah, and then you'll have delta omega over delta t, and nah, I don't know.
Wait, what's this m? Oh, that's the m mass of the disk. Okay. So no, I can't just put that back in because that'll be something else. So.
What's get the equation angular acceleration equals tangential acceleration over r?
This here? This equation?
Yeah.
What about it? What?
How'd you get this equation?
Oh, how'd I get it? Oh, sorry. So it's always if you have like a linear term, right? If you have a linear term, which is like tangential acceleration or velocity or what was it, force or something like that, right? Force is I guess a little more complicated, but you can convert linear things to the tangential, to the, what's the word? Rotational? No, not rotational. To the angular versions by just a factor of r. Right? So then I can just rearrange this for alpha.
Excuse me, Adam, what are the
Okay,
delta t and omega and alpha values?
Delta t is 10.
10 seconds,
Omega initial is 0. We don't know omega final, but we can probably find it. Could we? Yeah, we can find it. I don't see why not.
And what was alpha? Is it 0.25?
Alpha was 0.25.
Thank you.
Well, so what can I find with that? Yeah, I can find final omega. I always forget the words, but
How does that help with the mass problem?
I don't know, but that is just another number we can find.
If you were given the tangential force, would you be able to find the radius?
If I were given, well, yeah,
No.
like you're saying this. You're saying if I were given this, tangential acceleration.
I think I got it. We can find tangential force, right? Because we have acceleration and we don't have radius. Oh,
We don't have
so
radius,
annoying.
right? That's the thing that keeps screwing us up, right? Is that we don't have radius.
What if you had infinite correct answers? Would that mean that if you pick a random value between 0 and 50 and you find r, then they
Saying,
would be
because we
correct?
have,
Okay, yeah.
because we have inertia and we have alpha. Just find a value for torque and then substitute a value for like 10 newtons for force.
enough.
Find R, and that's one pair. Because they just want one pair. They don't want like all the
Just use
pairs,
the
right?
So
why don't we
true.
the final values, like just use the extreme values, just 50 and 3, and see what happens.
Well, extreme value is not gonna give you.
I see what she's saying. She's just saying decide on one value. Just choose one R and then find F or something.
Choose one. Do I know both these things? Yes. Yes, I do.
Yeah.
Oh, so I can just use
Yeah,
this.
you do.
Okay. Let's just choose F equals 25, I think. Wait, F goes from 0 to 50. Okay. F equals 25 newtons. So R times 25 equals that was 100 times 0.25, and then, well,
So it's 1.
it's just 1. R equals 1. Is that what they want us to do? I guess 1. I guess that is.
Do
a
we
pair.
have an answer to?
Let's see. This was number. For example, R equals if. Well, let's see if I do this. If f is 10, if I choose f is 10, then what would R be? It would be 10. Yeah, 2.25 or 2.5. I mean. Yeah. Which is what they got. Yeah. So that is what they did. That is what the solution is, right? So if I choose that, then I would get R is 2.5. I don't know why they got 2.51, but that's fine.
Maybe it's just a typo. I don't know.
So weird.
I mean,
And your alpha value?
For they got 2.51 for the R value at the end, not just 2.5.
But like, why? Why would they?
No,
choose
I mean,
something?
did you round your alpha value?
Oh,
Maybe
sorry.
that's why, I don't know.
Yeah. I did. Yes, I did round it. So,
yeah.
That's fine.
There's a problem.
Yeah. So yeah. Okay. Well, there it is. I guess since it was asking you to choose, it gave you the range of the things. I guess since it gave you the range, you can do that. Yeah, that makes sense. That does make sense.
But
If they
then-
didn't give you a range, there would be no way for you to guess because you don't know what's a valid option. Right.
But then, like, why is it that only 10 works? Like, how do they know which answer specifically
No,
we're looking for?
they don't. 10 is just the one they used. What we used 25 for, that'll work too. 20. We use 25, right? 10 is just I just used 10 again because that's like the answer. I want to make sure it matches up, so we're doing the right thing. But you can use any.
Okay.
Shouldn't the radius be constant though?
Well, it's not the radius of the disk. It's the radius of where you're applying the force, right? So maybe there's like a wrench or something like that has like you can change the distance of the wrench or something. Like the disk itself has a set radius, but that's not really what we're talking about. It can be applied at any distance ranging from 0 to 3.
Okay.
Right? So that's the difference there. Okay. There's that answer. Okay, well, it's 1 o'clock, so that's everything for this morning's session. We will have another session again. I can't remember. Was it at
6?
Did I say 6? Let's take a look.
I think so.
I'll just make sure, and then yes. So PCS 211 Wednesday at 6 p.m. Yes, and 62 people.
Like,
this is the highest one that people said they wanted to attend. So definitely we'll need the 2 server thing. So if we can do that again, 2 room thing again. So hopefully Manuel or
What time is it?
6 o'clock.
6.
Oh fuck.
Good luck with your CE and bro.
God damn it, man.
Well, can you not do it?
I can do it.
Okay.
It's just-
Okay.
All right.
Okay, but well, yeah. Or if you can if you can't, then figure out someone else if you can do it, right? Or I
That's
can
all right.
I can figure it out too. I don't know if someone just gives me some advice of how I should do it. I don't really know how though. So, but yeah.
You can
Yeah.
The way I did it.
Or we can host it
I'll do
on
it either
Zoom,
way.
though,
Don't
can't
worry. The way I did it is I made a second account and then I opened it on Chrome in Discord on Chrome.
That's what I was thinking.
So it's probably easier for you because you can just stream your screen.
Hopefully that works. Yeah. Hopefully it'll work to both. Yeah. Okay. I'll try.
It might not work because like maybe it can only record one like Discord. Like for me it works because I have 2 screens, so I stream one screen and then the
Yeah.
other.
Yeah. Well, okay. I'll try tonight, but like maybe someone should be available to do it.
I'll be here.
Okay. Sounds good. Sounds good for sure.
Yo, so like, so all the other things we did wasn't necessary then, that we did like the.
Well, all the other
Omega.
contemplating was not necessary, but we did need to find alpha.
As in like,
we had to find alpha. That was something we had to do, and that's what we did here.
and then we just substituted into the R alpha.
This is
It was
the main equation that was necessary. This is the main equation that was necessary. We found alpha separately.
Yeah.
You think we
to
can make
the-
like a Zoom meeting?
Well, the thing with Zoom meetings is that less people attend it because they don't see it in the thing, right? So we never hit 50 in Zoom meetings, right?
Yeah, we have
no difference,
we have a hookup, but it ends up being worthless.
right? Because just like people don't see it, so people don't come, and then there's no point in having a Zoom if it's like less people. So I think this is a better solution.
But this works. I think there's very little
delay or anything.
Thanks, Adam.
Can they also hear me in the other room? I assume so. That would be
Yeah,
that would be
they
bad.
hear you. They can't ask you a question, but
Yeah. Okay.
they can do it through chat.
Yeah.
So like we found the omega the alpha because with like kinematic equations the inertia was given to us, right?
The inertia was given to us. That's right. Yeah, 100. We knew it was 100.
Yeah. And then we needed to solve for R and F, and we just chose a random value for F and got R.
In the range that's acceptable. We know that it's acceptable between 0 to 50, right?
So yeah, but like for this question, literally any of those could work then.
Yeah. Any choice there would work. Yeah. And is my answer for A unique? No, it's not. Infinite answers.
So it's more like a guessing question. You just gotta.
Well, you gotta work out the math first. You gotta do some arranging, and then at some point you gotta just say, well, I have a range that's acceptable, so I'll choose something in that range, and I'll get something out in this range.
Or you can do the other way around, right? Like you can choose any value from 0 to 3 for radius. And
That's true. Yes, and self-ref. That's another way to do it.
Yeah. Okay.
Yeah.
Okay, guys. Well, I'm gonna head out. So that's it for me for now. I'll.
Good luck, you all.
Yeah. Good luck, everybody studying. Good luck on the
Thank
CN
you,
exam.
Adam.
No problem, of course.
You CN.
Don't forget CN.
Don't forget
Any
CN.
tips for this? Any tips
Do
for the
the
CEM?
pledge. Do the exam.
Yeah. Just do it and put the
Don't use
academic
the
honesty pledge because it's useless.
Don't use your notes.
What'd you say?
Yo, try to
Don't
memorize
use
some.
the internet. Don't use your notes.
Yes. Yeah.
Speed run it, and when in doubt, always choose C.